they've mandated vaccines. So yeah, we're still allowed to go into the office.
Okay. It looks like the new variant is here to stay.
Hopefully it's
becoming less severe.
Yeah. A lot of people are getting booster shots here, but I don't think that started in India yet.
Yeah, no, I think we are just on 2 shots. Okay, so it's 9:31. Alok.
Yeah, please go ahead. I think we should start right away. Okay, it's 31, you said. Okay, maybe 2 more minutes. Sorry.
2 more minutes, yeah. Actually, you can remove me as co-host because I don't have any co-host duties.
Yeah, but you're easy to trace if you're on the top.
Ah, okay, I see.
Simple as that.
Yeah, it's just that whenever someone enters, it pops up on my screen.
Okay.
Get distracted.
Yeah. Okay, maybe that could be disabled.
I doubt it.
Okay.
Maybe. Yeah, if possible, then go ahead. Otherwise, it's okay. Because my initial reaction is to just click the cross.
Right.
I don't want to deny anyone admission.
Yeah. Maybe one can start, Abhijit.
Okay. Hello, everyone. Welcome to the morning session of the 5th day of the Indian Strings meeting. Today in the morning, we will have 3 talks, half an hour each. First by Akshay Yelleshpur, second by Koushik Ray, third by Arnab Rudra. So each of the talk, we will roughly split as 25 minutes for the talk and 5 minutes for the questions. So please interrupt if you have urgent and short questions. Otherwise, let's keep the questions towards the end of the talk in the allotted time for 5 minutes. Okay, with that out of the way, let me welcome Akshay Yelleshpur from Brown University. And he's going to tell us about deformed W algebras in celestial holography. Over to you, Akshay.
Thank you. Can you all see my screen?
Yes.
Okay. Yeah, first let me start off by thanking the organizers for putting together this conference and for giving me the opportunity to speak. It's really a pleasure to be able to join by Zoom. I'm going to talk about this paper that I wrote recently. This is work done in collaboration with 𝗦𝗲𝘀𝗀𝗶𝗿 and Yicheng Ren, who are graduate students here at Brown, and Professor Anastasia Volovich. To start off with, holography tells us to look for non-gravitational theories living on boundaries of space-times. So for the particular case of asymptotically flat space-time, this would mean the boundary at null infinity. And I'm sure you heard about this in greater detail in Laura's talk a few days ago. But the null infinity of asymptotically space-time has the structure of R cross S2. And it is this S2 which is commonly referred to as the celestial sphere. And there's also another fact that the 3+1 dimensional Lorentz group on the bulk acts as the global conformal group on this celestial sphere. So there's often a statement made that the S matrix is the only observable in quantum gravity. Whether you like it or not, it's definitely a good idea to look for a dual theory which reproduces the S matrix in flat space or in asymptotically flat space. And this has indeed been the driving force for many of us who've been working on scattering amplitudes in one form or another. But specifically, the proposal of celestial holography aims to construct a conformal field theory which lives on the celestial sphere. And this is called the celestial conformal field theory, or CCFT for short. And it has been known for a while now that the properties of scattering amplitudes in the deep infrared severely constrain the CCFT. And very early indications of this was that the soft gluon and graviton theorems that have been known for decades in the bulk, they are equivalent to certain ward identities of the CCFT. But this was only the tip of the iceberg. There are more recent results. There's an infinite tower of these soft currents, and it has been shown that they actually form a symmetry algebra. So the focus of my talk today will be this infinite dimensional symmetry algebra. And of course, most of this work was done at the classical level, and it's important to understand the effects of loops and higher dimension operators. I won't have much to say about loops in this talk, but I'll talk to you about some recent progress on understanding the effects of higher dimension operators. And we'll see that they constrain the spectrum of the bulk theory in certain ways. So here's the outline of the talk. I'll quickly review what celestial amplitudes are. I'll show you how we can use properties of amplitudes to obtain OPEs in the CCFT. I'll talk about conformally soft limits, which are related to usual well-known soft limits. And finally, I'll put these two together to show you how this forms a new symmetry algebra. And then I will talk about deformations of these symmetry algebras and the constraint that they impose on the bulk. Okay. So let's begin. The scattering amplitudes are usually labeled by momenta and spins of the particles involved. Now I can think of the scattering amplitude as a 4-vector, or equivalently, I can think of it as a 2x2 matrix. Now the determinant of this matrix is the norm squared of this vector. So for null momenta, I can decompose the 2x2 matrix as a product of two column vectors. And these column vectors, lambda alpha, lambda tilde alpha dot, are called spinor helicity variables. Now, this decomposition is, of course, not unique. I can rescale lambda, lambda tilde by opposite phases, and this still leaves the momentum invariant. I can use this redundancy to further parameterize lambda and lambda tilde in terms of an energy, omega, and a coordinate z, which points a direction of picks a direction of the null momentum. And this is also happens to be a point on the celestial sphere. Now this epsilon is just plus or minus 1 and tells you whether the particle is incoming or outgoing. Now the Lorentz group of the bulk acts as SL2C, acts as the group SL2C on the indices alpha and alpha dot. And we can use this to work out how omega and z bar transform under the Lorentz group. And what we find is that omega transforms into this scaling, and z transforms into as a Mobius transformation. The way we usually construct scattering amplitudes, we take these one particle states, which are labeled by an energy, z bar, and helicity. I'm using S here for helicity for reasons that will become obvious later. And there's a good reason we use these states. These are eigenstates of momentum, and they make the translation invariance of the amplitude manifest. However, if you're looking at a conformal field theory, these states don't transform nicely under conformal transformation. Indeed, you can see here that omega picks up this extra factor. But we can make this better. We can define a superposition of these states, and this is nothing but the Mellin transform with respect to the energy. And these new states, I will call them as conformal primaries, And we can easily see that they actually transform well under conformal transformations. This is because omega transforms this way, but I have integrated over omega, and I can just redefine the variable to scale out this overall factor. So I can now instead label my states by a conformal dimension delta and a direction on the celestial sphere as well as the spin. So in particular, if I use the Mellin transform for the in and out states of the amplitude, I get a new object, and this is what is referred to as the celestial amplitude. This is basically the Mellin transform of the usual momentum space amplitude. And by construction, this new object transforms as the correlation function of n primary operators having spins Si and conformal dimensions delta I. At this stage, I can already point out a difference between flat space holography and ATS-CFT. The dimensions delta I are not related to any property of the bulk. But I can identify the celestial amplitude with this correlation function of n operators, which have conformal weights hi and hi bar related to the conformal dimensions and spins. And the claim or the conjecture is that there is a conformal field theory which lives on the celestial sphere. This is called the celestial conformal field theory, which computes these correlation functions. And if I knew what this conformal field theory was, I just had to compute the correlation function, and that would and inverse Mellin transform it to get the amplitudes in momentum space. Of course, we are still very far away from actually knowing an example of a celestial CFT. And I'd like to tell you why it is so. You might think, oh, I know 3 and 4 particle scattering amplitudes. I can just compute the 3 and 4 point function in the CFT, and I'm more than halfway there. Well, it's not so simple because I can Mellin transform the 3 and 4 point scattering amplitudes, but the resulting celestial CFT correlators are distributional. So there are these delta functions for the 3-point amplitude. I get delta functions of z bar. For the 4-point function, I get a delta function of the cross ratios. This forces the cross ratio to lie on a circle. However, all is not lost. We can still use many properties of the scattering amplitudes to deduce properties of the CCFT correlators and also about the spectrum of the CCFT. And in particular, I'm going to be talking about collinear limits of amplitudes and soft limits. So let's first look at collinear limits. Scattering amplitudes have well-defined collinear limits. If I look at the dot product P1 dot P2, you can see that the momenta are collinear whenever the point Z1 approaches Z2 or Z1 bar approaches Z2 bar. So if you're thinking of this as in terms of the celestial sphere, the points Z1 and 2 approach each other. So it's natural to expect that this limit has something to do with OPE. And let's start with the amplitude itself. I have an n particle amplitude. I know that in the collinear limit, it factorizes. In particular, this is true at tree level. In particular, it factorizes into a 3-particle amplitude times n-1 particle amplitude. And this is the picture, and this is the same in equations. Now I can obtain the celestial analog of this just by Mellin transforming both sides. So the collinear limit is reached by parameterizing the energies in terms of a variable t and also a common energy omega. The only thing I need here is the 3-particle amplitude on the right-hand side. I'm assuming, of course, that the exchange particle with momentum p is massless. So this is a 3-particle amplitude involving all massless particles, and it's completely fixed, uniquely fixed by Poincare invariance. So throughout the talk, all of these objects without the tildes on them are momentum space amplitudes, and if they have a tilde on them, they're celestial amplitudes. So the 3-particle amplitude in momentum space is completely fixed by Poincare. So let's begin. The Mellon transform of the left-hand side is nothing but the endpoint celestial amplitude. Now we can look at the right-hand side. Well, it almost looks like it's related to the n-1 celestial amplitude, but not quite, because the variable z bar 2 is shifted by some amount. But I can always just Taylor expand. When I perform the Taylor expansion, I can do the remaining integral over t, and the expression that I get, I've written down here. Now, let's back up for a second. What we did was we started with the endpoint correlator, which was the endpoint celestial amplitude, and we took this limit where z1 approaches z2, and I was able to rewrite it as n-1 point correlators, where I replaced operator 1 and 2 by some operator with a different conformal dimension at the point 2. Now, this is exactly what the OPE is. I can now strip off the remaining operators in the correlation function. I can clean up some of the variables, and I can just rewrite the whole thing like so. And you notice there was a beta function here, b of the conformal dimensions, and that is in the OPE coefficient, C alpha p. So now I'd like to talk about some features of this OPE. You can notice that the OPE coefficient is a beta function, which means it has a pole whenever either of its arguments is a negative integer, or 0 or a negative integer. If you're specializing to the case of Yang-Mills, S1 and S2 is 1 and P is 0. This means that the OPE coefficient has poles at delta 1, delta 2 being 1, 0, -1, and so on. And this contribution that you see here, labeled by P, is a contribution from a specific 3-point amplitude in the bulk. And that is reflected in the fact that there is a specific coupling constant here, kappa S1, S2, and P plus 1 minus S1 minus S2. This is the coupling constant of the 3-point amplitude of 3 massless particles with spins or helicities S1, S2, and this. So every massless amplitude in the bulk contributes to the OPE coefficient. But the good news is that there are only a finite number of interactions in the bulk. This is if you're ignoring the existence of massless higher spins. There are only a finite number of interactions in the bulk, and there are only a finite number of singularities that can arise in the OPE. But let's also focus on, for the moment, let's focus on the poles that the OPE coefficient has. And let us try to understand where they come from. And this leads us to the other kinds of special behavior amplitude, which is soft limits. So any tree amplitude can be expanded in a Laurent series around one of the particles, let's say 𝜔1. The soft theorem tells us that the leading divergence at low energies is 1 over omega. And beyond that, there are no, that's the leading divergence, and the rest are just polynomials or positive powers. So now I want to look at the behavior of the celestial amplitude as delta approaches an integer value k. And this must vanish unless the celestial amplitude itself has a pole here. And indeed, we can exchange the limit and the order of integration to see that this can actually be written as a residue of 𝜔1 to the minus k times the amplitude. And it picks out a specific coefficient in this Laurent expansion. So this tells me that the celestial amplitude itself has poles at these specific values, k equals 1, 0, -1, -2. And these are called the conformally soft limits, specifically because k equals 1 picks out the coefficient of the leading divergence, and k equals 0 is the subleading divergence. Now, clearly there are an infinite number of poles, and the residues of the operators on these poles form currents or behave as currents in correlation functions. And now the route towards these current algebras is clear. We start with the OPE that I derived. I take the residue on these poles. That gives me the OPE of these soft currents. And then I can look at the algebra formed by their modes. So that's what I'm going to do. I define these soft currents to be the limit where the conformal dimensions take on these specific integer values k, which is 1, 0, -1, -2. And let me work out the OPE when both of these operators are these soft operators. So let me restrict to the case of pure Einstein gravity, which means the only 3-point amplitude in the bulk is this amplitude coupling two positive helicity gravitons to the negative helicity gravitons. This is the MHV amplitude in the bulk. So there's only one coupling constant which appears on the right-hand side, and the OPE can be written in this form. Now I can extend this by adding other interactions in the bulk. Particularly, I can turn on an R-cube interaction, and the effect of this is that it introduces a new 3-point amplitude coupling 3 positive helicity gravitons, and that is the coupling constant you see here, and it introduces a completely new singularity in the OPE. And the claim now is that the modes of these currents form a symmetry algebra, and the path from OPEs to symmetry algebras is quite well known in CFDs. I won't spend too much time on this, but the basic strategy is I take these currents, I mode expand them. The modes can be written as contour integrals of the current itself. Now I could go ahead and compute the OPE. I could compute the commutator of these objects, which I call H. But with my hindsight, I know that rescaling them in a specific way produces a much simpler result. So rather than compute the commutator of H, I will compute the commutator of W. And the commutator can be written in terms of these contour integrals, multiplying them over the product of these two operators. I can now use the OPE, and the Z1 integral in particular will pick out the pole of the OPE. And when I do the computation, the resulting commutator looks like this, where N has this rather complicated structure. But of course, if this object has to be a symmetry algebra, it must satisfy the Jacobi identity. And so let's again go term by term. Let's start with pure Einstein gravity. Again, there's only one 3-point amplitude in the bulk, and the resulting algebra was computed a couple of months ago by Andy Strominger. And this algebra is the structure of this algebra is well known. This is known to be the little W infinity algebra, and this algebra has been studied quite long ago. And it turns out that there's no issue with this. You can check that it satisfies the Jacobi identity. But we're interested in what happens if we turn on higher derivative, higher dimensional interactions. In particular, we again consider the R-cube interaction, and the extra term in the OPE that I introduced here will again contribute to the integral, will again contribute to the commutator, and I pick up another contribution. However, if I now try to check if the Jacobi identity is satisfied, it turns out that that is not. It's just flat out non-zero. But this is not too bad because, as I told you, there are only a finite number of interactions that can contribute, and it's possible to check whether we can add extra terms or extra amplitudes in the bulk, which makes the commutator vanish. And for this specific case, it turns out that the only combination that works is if I add a scalar in the bulk. And in particular, I add a amplitude which couples to gravitons in the scalar. This would be like an r²ϕ interaction. And this couples to scalars and graviton. This is like an r⁵² interaction. And I can compute the resulting commutator. And it turns out that the Jacobi identity is satisfied only if the coupling constants satisfy these specific relations. Now, you can immediately see that if I turned off these interactions, I would go back to the previous case, and all of these commutators, all of these constraints are trivially satisfied. But with these higher dimension operators, these commutators are not the Jacobi identity is not easily satisfied.
Hello, Akshay. Sorry
yes.
to disturb. You are 20 minutes into the talk, just to let you know.
Yes, I'm almost done. Thank you.
Okay, sure.
And it turns out that if we include gluons into the mix, we get a lot more constraints, not only on the coupling constants, but also on the kinds of particles you can actually have in the bulk. And so, yeah, this brings me to the end of the talk. We've showed that the behavior of the amplitudes in the IR constrains the CCFT. In particular, minimally coupled Einstein-Yang-Mills and Einstein gravity and Yang-Mills enjoy an infinite dimensional symmetry, which is called W1+∞. The situation is not so clear when we deform these theories. The symmetry is deformed by high-dimensional operators, and if we demand that the resulting algebra is still satisfied, that it still obeys the Jacobi identity, we end up with constraints on the coupling constants as well as the spectrum of the theory. Now, the natural question to ask is these constraints, is there any theory which actually satisfies these constraints? Or what are other kinds of theories which satisfy these constraints? And also, ultimately, what happens when we take loop corrections into account, and if these constraints still remain to be true, or do they get modified in some way? Yeah. Thank you.
Thank you very much, Akshay, for a very clear, interesting talk. So you did very well on time. We have some time for questions. So Loga, go ahead, please.
Hi. Thanks for the talk. So there are some things I did not quite understand. So these kappas that with these three coefficients that that you were talking about. So you are constraining them. So do you understand that right? That they have not been like computed in any realistic theory. Let's say some low energy limit of string theory or something. Is that right? Has it not been computed in any of these theories, any higher derivative?
Well, these kappas are just the coupling constants of the 3-point amplitudes.
Okay.
So if you're asking, is this relation satisfied in any low energy effective action of string theory, that's something we still have to check.
Okay.
But as of now, it doesn't seem like it's a very easily satisfied constraint. We haven't checked, for example, we haven't checked bosonic string theory, but we have checked, we managed to find that conformal supergravity for some reason satisfies these constraints. So we're still trying to figure out whether this is a generic feature or this is something very special.
Maybe let me just ask a simple question. Let's say you have a Yang-Mills theory coupled to some matter, some scalar matter, let's say fundamental scalar matter. Do you have constraints for them? I mean, this was all for gravitons.
If you just have Yang-Mills and matter, then there are no constraints. Okay. But if you introduce F cube interactions, then you find that there are constraints relating the coupling constant of the f-cube term and the scalar couplings.
Yeah. This is a bit confusing, right? I mean, what are these constraints? These are different from unitarity constraints, is that?
Yeah, these are definitely different from unitarity constraints. I don't have an intuition as to where they arise from. At the moment, I should say that it's not very clear how seriously we must take these constraints. It's possible we should. I still don't know what happens when loop corrections are introduced.
No. I mean, at tree level, one can just ask. I mean, Jacobi identity is a mathematical statement, right? It's not some.
Right.
I'm a bit like if you write down let's say W as operators, and then you say its commutator is such and such, then what does it mean to say if Jacobi identity is violated? I think that can only mean that W is probably not an operator or something, or its product is not associative or some.
It probably just means that this is not a symmetry of the theory.
This I don't understand, because I mean it may not be generators. Okay, so W might not be generators and so on, but if you just take any operators and you write A comma B equal to C, I mean, even if they are not symmetry generators, they should be Jacobi, right? I mean, or am I wrong? Like, I understand this point of view that probably the W symmetry is broken or deformed or something, but unless you have a really funny product on the operator algebra, how can you violate Jacobi?
Loga, can I just add?
Yes.
Yeah. So the way he has constructed these W's, the non-satisfied. I mean, if the corresponding Jacobi is not satisfied, then it would mean that those currents, the way it has been defined, is not a symmetry in presence of the higher derivative term. That is what I would think that it would be.
No, my question is just simple. Whatever way they're defined, W is defined in some way. And if its commutator is calculated, it should be Jacobi, right? What does it have to do with that being a symmetry? This is what I don't get.
No, but if it is a symmetry, and if that, I mean, if that is satisfying a particular algebra, then that algebra has to satisfy Jacobi also, no?
Even if it is not a symmetry, I would say Jacobi should be satisfied.
Loga, I think that, sorry.
Loga, I think this is not, you're right, of course, but this commutator is not defined by taking W as an operator, I think, but you are giving a prescription using the OPE to define this commutator. So it is a priori not obvious they will satisfy Jacobi. It's not, as you are saying, it is not.
So exactly. I think the point is whether it closes on this subset of the this thing. These W's are defined in some particular way at some moments, and the question is whether the OPE closes in associative way on these particular moments of currents.
It depends very heavily on the structure of the OPE.
Okay, so maybe if I just understand these answers, you're saying the OPE might not define an associative product on this.
OPE restricted to these currents.
Yes. I think currents might not define an associative product, and that's what one is checking. These are the constraints that it is associated. Is that?
I think so. Yeah. Because
in fact, sorry, just I think I would say that even if these constraints are satisfied, there is a prescription, right, Akshay? That I mean, if you had if you were not in MHV setting and you had both holomorphic and anti-holomorphic poles, then I think in general your choice of contour to define this OP would tell you that the Jacobi is satisfied or not, right? I mean, is that?
Yeah, in general, because we have both a holomorphic and anti-holomorphic, we are specifically picking only the holomorphic poles.
Yeah.
So
if you choose some arbitrary contour, you probably won't even have the Jacobi even then, right?
If we mix the holomorphic and anti-holomorphic, then it definitely does not satisfy. Even even without higher derivative corrections, even then it's not satisfied. Yeah.
Okay.
Hello, did you ask your question?
Yeah. So hi Akshay. So one question I had was that in the old Strominger story, there was a relation between the two soft currents, right? The positive and negative helicity soft currents were not independent because there was a linear combination which decoupled from the S matrix. Right. This gravity, these are the CK constraints. Yes. So I just maybe miss. I mean, that should be true here also, right? That the leading soft gluon currents and soft graviton currents are not, for the two helicities, they are not independent of each other. Was that constraint, is it implicit or something we have to impose additionally?
You mean the decoupling of the null states?
Yeah. I don't know this very well. I mean, I'm saying from the perspective of the soft theorem, remember that the two soft gluons or soft gravitons are not linearly independent. There's a linear combination which decouples from the S matrix. Right? I mean, there is one word identity, but two soft theorems, but that just tells us that the two soft theorems are not linearly independent. So maybe
right.
Yeah.
I haven't, I'm not sure how to check that in here, because we specifically, the prescription we have is such that, for example, if you were to compute the commutator of two W's with negative helicities, it just vanishes because we are not picking out the anti-holomorphic pool at all.
I see. Okay. Abhijit, sorry, just one small question can I ask? Just
okay.
Yeah. So Akshay, so your collinear factorization was, as far as I understand, was kind of key, right, to derive these OPs. Yeah. I mean, if you go beyond tree level, we know that, like in QCD, we know that collinear factorization is violated because of this presence of this what are called Glauber gluons, right? So I don't know. I know you have not looked at loops, but is there any thought? What if the collinear factorization was not valid? I mean, which we know is true in QCD, for example. How this OPs will be defined? I mean, this is a very general question. Just if you had.
Yeah, I haven't thought about it actually. Even at loop level, we were trying to think about how to even define single soft factors, because these mode expansions are not valid once we introduce log corrections. So we haven't thought about this yet, we have not made any progress.
Yeah, I think we should postpone the rest of the questions to the discussion session. So let's welcome the next speaker now. Akshay, if you could unshare your screen.
Abhijit, sorry, I just want to point out that today's discussion session is going to be a little different from the ones we've had. It seems Subrat is going to lead a discussion on a topic.
Oh, that's right. That is
so
correct.
Perhaps that could be factored in.
So let's have a couple more questions. Two more questions. I guess Somdatta and then Rajesh, and then we will move on to the next speaker.
Yeah. So could you go back to the slide where you define the Mellin transform?
Sure. Here.
Yeah. So, yeah. So the point of defining the Mellin transform, I guess, was to see how a conformal field theory dual could arise, right? Because that's how you got the deltas and so on, right? Because otherwise,
the point here is that omega picks up this rescaling factor. So if I were to just look at these states, they don't transform nicely. But here I can just redefine omega and pull out this factor. And I couldn't identify omega with a conformal dimension, but here I could identify it with a conformal dimension because it doesn't change under the conformal transformation.
Yeah. So the whole point is to try to reformulate it in terms of some conformal field theory. That is why you are doing it, right?
Yeah, we're changing the basis of scattering amplitudes and rewriting them in this new basis so that they look like conformal correlation functions.
So my question is, like, maybe you don't try to define the boundary theory, the celestial theory, as a conformal field theory, but just as some plain old field theory, and try to see what happens. Because once you can you go to the next slide?
Yeah.
The next one. Yeah. So because of defining it as a conformal field theory, you are getting these delta z's, right? And that was the problem. So if you instead of defining it as a conformal field theory, if you just left it in terms of the omegas, maybe you
sorry, Somdat, I think it's better if you give the suggestion to the speaker over the email. We'll go to the next question. Rajesh, please.
Hi. Thanks for a clear talk. I was just wondering, the W infinity algebras come in a one parameter family, the so-called W infinity of lambda, where lambda can be a complex number in general. And the W1 plus infinity that you mentioned of Strominger and so on is a specific point, probably lambda equal to 0 or lambda equal to 1. These are actually the only points, more or less, where the algebra is a kind of a conventional Lie algebra. At any other value of lambda, so even infinitesimally away from the free fermion, free boson W infinity algebras, the algebra is nonlinear in the sense that there are product currents appearing on the right-hand side. And that's necessary for the closure of the whole algebra. So I was just wondering whether maybe there are subtle terms involving products of currents, which maybe you have not yet seen, which are perhaps what might be important for closing the algebra. In fact, I would imagine that's the most natural deformation of the W infinity algebra away from the Einstein gravity point, because the rest cannot be W infinities in a conventional sense, or they must be related to it by a field redefinition if you have a linear algebra. I was wondering you had any thoughts or comments.
Yeah, the initial thought was the little W infinity would get deformed to the well-known big W infinities on when we introduce these corrections. But I guess a fundamental difference there was the way that was derived was we have a bunch of modifications to the little W infinity, and we demand closure. But we also demand that the algebra, that we demand the sort of a truncation, and that uniquely fixed that to be a one parameter family. But here we are naturally setting the coupling constants of involving higher spin massless particles to 0. So somehow maybe that it evades the, this is still not very clear to me, but it's possible that it evades the one parameter deformation rule.
So are you saying that the higher spin currents here will be, it will not be sort of, there'll be a proliferation of higher spin currents? Because I thought the usual W infinity of lambda is just based on the fact that, let's say the simplest case, you have one higher spin current for each spin, and then you consider its moments. And I thought if you have that tower, then more or less it's kind of unique to this the same, but there might be loopholes I'm missing.
So I think the point was that the commutator of two of these higher spins involved they started off with an ansatz. The commutator of these two W's involved a sum of W's of lower spins, and unless the coefficients appearing on the commutator imposed a truncation, you would end up with these currents with negative spins. So the coefficients were engineered to specifically produce zeros, and I think that is why you have these 3f4 hypergeometric functions in the big W infinity. But here, just the absence of the higher spin. Here, when I'm saying spin, I mean the usual Minkowski spin. The higher spin massless particles, just having them to be 0 somehow evades this. So actually, if you look at the structure of the algebra we found, This polynomial n is one factor which appears in the big W infinity, but the big W infinity is also multiplied by a hypergeometric function which is absent here. So yeah.
Okay. All right. Thanks.
Okay. Thank you, Akshay. Let's now have Koushik share his screen. So Koushik, I will let you know when you are 20 minutes into the talk.
Okay, so I'm audible and visible, right?
Yes, you are. So welcome, Koushik. We are very happy to have Koushik Ray from ICS, and he's going to tell us about Quaternionic Lauricella-like systems and conformal integrals. So over to you, Koushik.
Okay, so let me first start by congratulating and thanking Alok and his team for putting a lot of effort into this conference, which is already showing by the smooth running of the conference. And let me also thank the other members of the NOC to give me this opportunity to speak. So today I want to discuss this Quaternionic Lauricella-like systems and conformal integrals. This is a work done with my graduate student 𝗰𝗵𝗶𝗶 Pal, and the references are here. This is so, as I said, so this is a computation of conformal integrals. So this is basically really an exercise in calculus. So so let me start from the with some. So I'll start with some motivation discussions. Let me just make it presentation. Yeah. So here's the plan of the talk. So the desideratum is so this is in CFT. So we'll be desideratum is to obtain the correlation functions. So I'll start with that. Only in this half an hour, I hope to get up to half of this computation, which is the conformal integrals, and then I'll recall the conformal groups, and then I'll talk about the two-dimensional thing, which is very well known, and how Lauricella system appears, and then we'll generalize this to 4 dimensions and obtain Lauricella-like systems, and then I'll summarize. So so this is really redundant for this audience, but let me just start with this thesis notation as well. So so if I have a group, that symmetry group that acts on a space-time, some space-time M, then one can, and I have a quantum field theory whose partition function is given by this with an invariant action and this host terms. Then we know that the G acts on the fields as well as the currents, and the correlation functions, which are moments of Z, are actually given as these are covariant with respect to this this group G, and so therefore correlation functions are obtained as representations of G for n different points, n points which are space-time points in the this x1, x2 is they belong to M. So basically a correlation function is can be obtained starting with representations of this so-called symmetry group. So that's what, and the group in question for us today is a conformal group. So let me just recall that. So start with M, which is a Euclidean, we'll take this as a Euclidean space in n dimensions with a quadratic form given by this, the usual one. And we know that a conformal transformation is an angle preserving transformation of M to itself. And if it's an orthogonal, we also know that a map which is orthogonal is orthogonal, or a non-zero real multiple of an orthogonal transformation is a conformal as well. So that we know, and this is the usual way of implementing the conformal group in quantum in conformal field theory. So you start with this M, which is Rn for us. Then you have this map. Everybody has seen this map. That so that maps it to this manifold M circ with 2 extra coordinates x, u, and v. So these are the u. This one is u, and this is v in this for this map. So, and in this M, you consider a homogeneous equation of these variables, which defines a projective manifold inside M circ. So then this is called a conformal compactification. This is within the projective. This is a projective compactification, and so this is called a conformal compactification of M. And from here I can also go back the image. So this is the image of I, which is may or may not be a proper subset of the conformal compactification. From here I can project it back to M. So a conformal transformation is typically obtained as this map. So first operate with I, go to M circ, take orthogonal transformations here, and then project it back. So this is what it is. So first I, then T, and then pi, and this I induces an injective map, of course, from M to this conformal compactification. And this conformal transformations, as you see here, so here pi Ti or IT pi for that matter, in that order, they're in 1-to-1 with the orthogonal transformations T of the null cone, which is a conformal compactification in 2 higher dimensions, which is in X, U, and V. So this is the usual way of implementing conformal group in conformal field theory. And the conformal group of M is defined as the connected component containing the identity in the group of conformal diffeomorphisms of the of C, the conformal compactification that I just defined. And this is by Liouville theorem given by the Mobius group. Everyone knows about this. So, and the conformal group of R4, that is the what basically is our interest today, is SL2H, H being the set of quaternions. So this is, as we'll see, this will be this action of the conformal group in R4 will be given in terms of SL2 valued in the quaternions. As an analogy, for R2 we know is much more complicated. All we'll use for the, today is the group SL2C acting on C by Mobius transformation. So I'll start with that and define or describe the Lauricella system in this particular case where I have SL2C in R2, and then I'll generalize to the 4-dimensional case. Now, coming to the representation. So now, as we said, so in a conformal field theory, if I want to find out correlation functions with a symmetry group, which is a conformal group, I need to construct representations of the conformal group. Now, just to recall, the representation of G for any group for that matter on a manifold that acts on a manifold is given in terms of so-called good functions. We have to define what good functions are. In some cases, it can be analytic functions. Some cases it might be smooth functions. So if it acts on the manifold, it has an action on the manifold, then one takes good functions which are covariant under this group, and that defines representations of the group. Now, for n different points on M, there are 2 things to consider. The usual way of going about this problem is take the tensor product of representations of G on the manifold. For example, take the conformal group on M, Ra or Rn, and take the write down the representation, take the tensor product, and most of the results that we have been obtained using this method. So today I want to do this computation, and also there's some advantage of this. Not using this tensor product, but first going over to the so-called configuration space of n points on the manifold. So this is we know from classical mechanics. So I have a n number of points moving around in a manifold, and I can talk about the configuration space of n number of points on this manifold, and then look for good functions on that configuration space of points of M, and then try to look for representations there. So that's the strategy for today. And for the configuration space of points, we'll need to choose a model, because we'll be talking about integrals in this. So the required kind of compactification or completion of the space, and I'll define this. So I'll take what is called a Fulton-MacPherson completion of configuration space. I'll define this later. So that is more or less the wisdom that I have about this, and now I'll show you formulas. So now over to Lauricella systems in 2 dimensions. So on the on this configuration space, which in 2 dimension is also essentially coincides with the projective compactification. So let me not complicate matters for 2D. So here in the configuration space of n number of points on see, I have this n number of points z1 to zn, one can define this integral. Mu's are called weights. Mu's are typically between 0 and 1. And this integration is over a contour from one zi to another zj, such that that contour doesn't include or enclose another third zi. Now, if you define this, these are invariant under translation. It's clear by of z by a constant. These are also homogeneous of degree 1 minus sum of mu. And these are germs of Lauricella functions. Lauricella functions, as we know, are generalizations of hypergeometric Gaussian hypergeometric functions in multiple variables. First one, if it's one variable, we call it hypergeometric. In two variables, we have 4 Appel functions, and the 3 and onwards are called Lauricella in general. This, oops, sorry. Yeah, so this integral obeys a differential equation. This is of the Lauricella system. This equation is actually obtained by very simply by taking derivatives of I, this integral, with respect to zi within the integral sign, and using this identity. This is a trivial identity actually, where in this I have denoted z I minus zj as zij. So this is, you see, a second order differential equation in terms of this where the variables are zis, and this is called a Lauricella system, and yeah, the solutions are called Lauricella functions. And we want to, so these are good. We claim that one knows that these are good functions on the configuration space, and we want to find out representations of SL2C out of these guys. So the action of SL2C action is Mobius, and the Mobius group acts on the correlation functions as this. So I have an endpoint correlation function that goes over to transforms with these factors coming from the denominator of the Mobius, CZ1. For each of the points, I have one factor, and with some conformal weights, capital, which I'll denote by capital deltas. So this is how it transforms. Now you can check that under this Mobius transformation, the Zij, which was Zi minus Zj, transforms as this with a weight 1 or minus 1. And I mu transforms as this with the mu's coming up here, provided I have sum of mu equal to 2 and the degree of homogeneity then is minus 1. This also incorporates the point infinity, and so this didn't have the infinity. So when I try to, when I make it the sum of mu's to 2, it incorporates infinity. And at this point, I call I mu, this integral, the conformal integral. And now holomorphic representations of the Mobius group can be constructed out of, you see, these Zij's and this I mu. That's clear. Now I'll take certain powers of Zij and certain powers of and start with and multiply with I mu, and I can always construct representations of the conformal group in 2 dimensions, the Mobius group in 2 dimensions. And here are examples. This is the for n equal to 2. The only allowed mu's are 1 and 1, and you have this degree of homogeneity minus 1. For 3 is the usual results follows. And as everyone knows that for higher than 3 points, there's invariants called cross ratios which complicate this matter. So let's define something called chi ijkl as this combination. This can also be written in terms of another kind of variables. I'll come back to this later. This is called a variables ij by ik. Right. So these are invariants of the Mobius group. That if you go back to the transformation, you see that Mobius group acts by on ij as I and j. And if you see here, I have one I1j here, one I1j here, so that cancels, and this is true for every index. And you see here in the 3 and 2 point functions, there was no conformal integral. 4 onwards, the conformal integrals appeared. Now I have to basically solve. So if I wanted to, here's the point. I want to evaluate or obtain the Lauricella functions, and to do that, one defines. Now, out of the chi's that I defined, these ratios, not all of them are independent. They have relations between them. So suppose I define the independent cross ratios with another symbol psi, and there'll be a certain number of them. I will so that number of xi's is given by this index A. So I have, and xi's are defined by zij to the power alpha ij, and alpha ij is symmetric, and then has this condition that the sum is 0, that gives the scale invariance of zij, invariance of this and the Mobius transformation as well. And here's the integral, and as we said, this integral is a good function on the configuration space. I can, and so this, and now I promoted it to a representation of SL2C. So I take this ansatz that it's given actually by a function of the invariance xi's and some factor zij to the power beta ij, so that and beta ij's are constant to have appropriate transformations under the Mobius. But remember, this beta ij's are artifact of the ansatz and shouldn't appear in the final formula, and that we'll see that that's the case. So it has beta satisfy some constraints related to the mu's themselves. And now if you plug this in, this xi is and this ansatz in the Lauricella differential equation, you get this. This is complicated. I don't want you to remember this. Only thing to see note here is that this is given in terms of the alphas, which are the indices of the invariance, betas, which are here in the ansatz of the conformal integrals, and this is a second order differential equation in terms of xi's, the cross ratios, and all the chi's which are invariants are either xi's or their functions. So this is a well-defined set of second order differential equations, and they can be solved in cases like for the n equal to 4, there's only one cross ratio, and you can solve it with conformal integral, 4-point conformal integral in terms of this zij to the power stuff and Gauss hypergeometry function. In the n equal to 5 case, you have two cross ratios, and you can solve the this in terms of this invariance. And so this is the invariant part, and this is the zij to the power beta part. These F2s are the second Appel functions. So you can solve it in terms of Appel functions, and there are four germs of this Appel function, and there are 4 arbitrary constants with which we can add them. In the correlation function, of course, you'll have to choose certain germs using the monodromy. I'll not get into that. The important thing to note here is that there's no beta, there's no allusion to beta in these formulas, only mu's, as one should have. So now with that, so this basically, this was to set up the Lauricella system and show that this in 2 dimensions, I have representations of SL2C in terms of these conformal integrals, and conformal integrals can be obtained as Lauricella functions. I'll now try to take this and use this as an analogy to work in 4 dimensions. So in 4 dimensions, as I said, the conformal, the Mobius group is actually SL2H, H being the set of quaternions. So now my space is R4 with an infinity. And these formulas that I have shown apply mutatis mutandis to 4 dimensions. The reason being, I can write a complex number Z as this 2 by 2 matrix, where X and Y are the real and imaginary parts of a complex number X plus IY. And that goes over to a quaternion. I can, so in terms of 2 complex numbers, U and V. Yeah, so I can take U as, if I write U and V as 2 complex numbers with Q0, Q1, Q2, and Q3, this also is 1-to-1 with a 4 vector, as we, this is also well known. And now here's a notation. The norm squared of this vector will be denoted, will be given by the determinant of this matrix, Q. And yeah, this is the usual notation, and this is the volume form. D, Q0, wedge 1, wedge 2 is 3. So with this, let me also recall how this conformal integral comes in the computation of correlation functions. So what you do is you start with the endpoint correlation function and then parse it in groups of 3 using this operator I, where pi's are projectors. You see that pi satisfies this relation. This is nothing but actually, this is actually can be written in terms of a shadow operator. I just chose to write both the integrals here so that it's slightly easier to work with this in this form, because I can choose to do whatever integral q or q prime as I want, depending on what I want to do. So if you did that, so start with the correlation function, parse it using this in terms of in groups of 3, you see that the correlation function has this generic form. It has factors of qij with certain powers, and this integral here I mu n in terms of q, where these are the q minus q1 determinant to the power mu1, etc. This is the volume form that I defined. Yeah, so this turns out to be generic form. Here you might have sums, other sums and integrals, etc. So what you essentially do is, after parsing, you have for each of the i's you have certain variables. Keep on integrating on those over those variables until you are left with a single integration variable, and then you get.
Excuse me, Koushik.
I'm sorry.
Just to let you know, you are 20 minutes into the talk.
Okay, so I'll try to. Oh, yeah. So here's the translation from the 2D. Oops. So this was the 2D conformal integral, which has now generalized to this. This was the identity that was required to derive the Lauricella equation, and here's the identity that generalizes to this. And this was the Lauricella system. This also, in the same procedure that I take derivatives of with respect to qi's here and use this identity now, and I get this. This is what I called a Lauricella-like system in 4 dimensions. This is not a Lauricella system. So I call it Lauricella-like, but the computation is exactly similar. So to summarize, we have these integrals. These are and they satisfy these differential equations. This is a Lauricella-like system. I have to now solve this. So now let me just give a one-slide introduction, definition of Halton-McPherson completion of the configuration space. You start with n number of distinct points on the manifold M, which is R4 union infinity for us. And then you embed this space into a space like this, where M, this is the n number of copies of the manifold M. Here I'm talking, we are in R4, so here's the S3, the 3 sphere, n by choose 2 of them, given in terms of these coordinates, and then these guys, which are given by the aij's that I introduced earlier, even for the in 2 dimensions. These are given by qij by qik, and now you see that it includes 0, so this gives you a compactification actually. Now, this is a description of the Halton-McPherson compactification of the configuration space. Now you see, I mean, we are talking. So I want to. So the integral I mu n is interpreted as a good function on this, and I want to construct representations in terms of those. Since this part will go away because I require translation invariance. This part will go away because they have qij's, and unless we have spinors or vectors, we will not require them. So everything will be described in terms of this aij case. So to see that, so here's the action of the conformal group. Now SL2H, H being so this A, B, C, D are in the quaternions in H, and the condition AD minus BC, the determinant condition, generalizes to this AC inverse DC minus BC, and the good functions on. So and you can also check that this determinant of Qij transforms like this, and mu I mu n also transforms with this, with now the condition and sum of mu tends to 4. And one can construct representations of SL2H out of this. And here are examples once again, that for n equal to 2 and n equal to 3, again, we have a very similar structure. For n equal to 4 onwards, we define again new quaternions, chi ij kl, and their determinant is an invariant. So this chi ij is, this is a quaternion, this is not a determinant. This is the determinant of this, and I can rewrite them in terms of these A variables of Fulton-McPherson compactification. And some of them, as before, are chosen as independent ones. So I choose the independent cross ratios as here with again an alpha satisfying the same conditions as before. And I also now I have interpreted this integrals, this conformal integrals, as good functions on the configuration space of Fulton-McPherson completion, and thus I can choose this answer. This actually, so the choice of answers is justified by the fact that we are working on this Fulton-McPherson completion of the configuration space. So I take this as this differences Qij to the power some beta and the invariant part. And again, beta is an artifact, it shouldn't appear. Now, take these answers once again and plug in the Lauricella-like differential equation. One can see that this is after doing that, after some calculations, the invariant part satisfies this differential equation where I have defined this Lig operator here. Again, only thing to remember is that this is defined in terms of the determinant of the invariance, the chi's, and the alphas coming from here, and the betas coming from the ansatz of the conformal integral. Yeah, so with a certain number of AB, which is I called N0, and N0 is actually n into n minus 3/2, and these are the logarithmic derivatives with respect to the cross ratios. Now, important thing is that there are n into n minus 3/2 equations, because Lij, if you interchange Lij, it gives the same equations, and the sum of them, this Lij operators is 0, so that takes away another one. So now there's an observation. The observation is the following. This operator Lij acting on the invariant can also be rewritten in terms of another set of operators with 4 indices now, and I have now defined theta ij as the logarithmic derivative with respect to the Qij, determinants of Qij, and one can write the Lij acting on the invariant as this sum of Lijk's acting on the conformal integral. I have written these two sums separately because it turns out that if you want to derive this relation, it's easier to first sum over this, then over this, and then subtract. Otherwise, you can prove it, it becomes just complicated. So now that essentially means if we can simultaneously solve these equations coming here, all of them, we have a conformal integral. So that's the interesting observation here. So I started with this equation. This came from the Lauricella-like system by putting in the ansatz, and then I rewrite it in terms of the sums, and from there I see that if I can solve this, all of them simultaneously, I have a conformal integral. So now this is done using some toric geometry. So let me just describe this in brief. That if you look at this transformation of the Qij's, see that Qij in the transformation has one factor which involves I, one factor which involves j, and the powers are -1. So I have written down this in a table. So Qij as it transforms, Q1, 2, 1, 3, and 1, 4 will have one factors in Q1. Q1, 2 will have a one factor in Q2, this one factor. 1, 3 has a one factor in 1, 3, not in 2 and 4, and so on and so forth. So this gives me a rectangular matrix all the time. This is n into n minus 1/2 by n matrix, determined by these weights of the Mobius transformations on the Qij's. The kernel of this, or the set of null vectors of this, give the invariance. And these are they determine the cross ratios. So for example, for this matrix, Mathematica gives you this kernel. It has 2 vectors in the, and I choose this as the basis. And the cross ratios corresponding to these are given by, these are identified as alpha. So Q12 with a 1, Q134 with a 1, 14 and 23 come with -1s. And similarly for the other cross ratios, Xi2. So I have two cross ratios for this case. Now, given a rectangular matrix of this kind and its kernel, there's something called a GKZ, Gelfand-Kapranov-Zelevinsky A hypergeometric system, which is defined in terms of this. Here, AI, JK are these components. So this is I, this is JK. So these are the differential equations. Alpha ij and minus alpha ij come here because so the positive components of alphas will appear here. The negative components of alpha will appear here. So that essentially means, so these are the positive components for this vector. These are the negative components for this vector. They will appear here and here. So the operators acting on F form an ideal in the Weyl algebra corresponding to the matrix of the toric data that I described. And again, now the observation is that given a rectangular matrix A with a basis of kernel, these actually imply this Lij K L acting on F is 0. So this is the same operator as this.
Sorry,
so Koushik, this is another observation.
Yeah, it's been 30 minutes, so please try to finish.
Oh, I'm almost done. Okay. Maybe, can I get 1 more minute?
Sure.
Yeah. So that I'm done. So basically this is what happens. So if you can solve this GKZ hypergeometric system, you have so this is the examples for this particular case, which is n equal to 4. You have four of these quaternions. It's the solution is obtained as this, which is a has this leg factors 1, Q, 1, 2, etc. And this is a function of the invariants. I have two invariants. I have this infinite series, which is a GKZ hypergeometric system. For 5 points, it's slightly bigger. There are 5 cross ratios, independent invariants. And this is given in terms is by this. In the paper, we also have given the case for n equal to 6, which is bigger. But generally, this is the pattern. This is the what you get in general. You can so these are the leg factors. There's no beta anywhere, only mu's, and n0 is this, and pn0 is always a series with a certain number of x's, which the n0 number of cross ratios. So to summarize, we have talked about conformal integrals, how it appear in the computation of correlation functions, and in 2D the conformal integrals transforming under the Mobius are obtained a solution to a Lauricella system. And in 4th dimension, we generalize it to a Lauricella-like system with a conformal group SL2 on the quaternions. Conformal integrals are now interpreted with, as a good function, and the choice of ansatz is justified by taking them on the Fulton-MacPherson completion of the compactification of the configuration space. The Lauricella-like system is solved using the GKZ A hypergeometric functions in general. So this is what we described. And this is the future in the future Lightcon. So we are now this one knows that this Fulton-MacPherson is also described in terms of graph complexes, and so we expect that this is going. This might have a role to play, might be useful in implementing Bootstrap. One most issue is that we have seen that from the kernel computation we have n into n-3/2 number of cross ratios all the time, but we know that for in d equal to 4 for n greater than 7. Greater than equal to 7, the number of cross ratios grow linearly in n rather than quadratically. So this supposed to probably mean relations among the cross ratios. We are looking into that. And thank you for your attention.
Thank you, Koushik, for an interesting talk. We have time for only one question. So Somdatta, go ahead.
Yeah, so could you go back to the slide where you gave the expression for the IN in terms of the integrals over the Q's for the SL2H system, for the 4D system?
Yeah.
Yeah. So here, how do you do these integrals? Because for the Z, if it was just Z, then you could have done it in terms of contour integrals. But how do you do the integrals?
Yeah, okay, that's an interesting question. So in principle, I should do this over a shell, but you cannot evaluate these integrals. That's the reason I went to write differential equations for this. And these are singular integrals. Now I have a differential equation, right? So I solve these equations and it's not a single valued function. This will have germs like Lauricella or hypergeometric functions. And this constructs a local system. Yeah. So I'm not going to evaluate these integrals. The integrals have to be interpreted as integrals over shells, but direct evaluation is very difficult. So yeah, that's why this whole technique.
That's correct. But for the Z system, for when you had the Z integrals, you had these identities in terms of the Z's, right? Which allowed you to write down this equation that you have, this differential equation.
Yeah. So I
what is the here?
Oh, sorry, I'm going the wrong direction. This one.
Okay.
So sorry, I went fast over this. So every relation translates.
So this identity satisfies even if you replace Z by the Q's.
Remember Q's are matrices, so they have to be in proper position. Yes. And that's why you see when I write down, take the derivatives, I have written the B, C, etc. These are the matrix components of the quaternions.
Yeah. Okay. Thanks.
Yeah.
So maybe one more question quickly we can take. Alok, if you can keep your question brief, please.
Yeah. Hi, Koushik. Thanks for the talk. I just had a conjecture, and I wanted your comment on it. This description that you have of these conformal integrals, the GKZ system and the Lauricella system, it literally seems to be crying out that there should be a map of this problem to a corresponding problem in algebraic geometry, where you rewrite this as the Picard-Fuchs equation for the period vector of a toric variety in maybe the large complex structure.
Yeah. I didn't want to get into that, but if you look at this, the form of this toric data that I'm writing, these are actually okay. One thing to remember is that these xi's we have are actually real numbers.
Okay, so this could be restrictions of the complex
that's
structure.
Right. But if I allowed complex numbers and use the same toric data, I would be doing what you exactly told, the periods of Grassmann variety. These are like embedding of certain number of depending on what number of rows you have, certain number of vectors in a P to Pn of some kind.
In fact, I would venture to say that this could be mapped to a problem of calculating a Picard-Fuchs equation from
these are the Picard.
Yeah,
these are the Picard-Fuchs equation.
Right.
Once I'm writing are the Picard-Fuchs equation in that case for this Grassmannian varieties given by this toric data.
Right. So the F could be mapped to actually a period integral expressed as a path integral using the 𝗰𝗵𝗶𝗶 description. So it could be a beautiful map. Okay. Thanks.
Yeah.
Okay. Thank you. Let's thanks, Koushik. If you could unshare.
Thank you.
Let's move on to the next talk. It's Arnab Rudra.
Yeah, I have to unshare, right? Somehow.
Yeah.
Let me try to share. Am I visible?
Yes.
Yeah.
Okay. We are very happy to have Arnab Rudra from 𝗰𝗵𝗶𝗶, and today is going to tell us about massive higher spin amplitudes in flat space. I will give you a notice when you are about 20 minutes.
That would be great. Thank you. Thank you for giving me this opportunity, and thank you for this wonderful conference. Today I'll be telling you about some very simple computation that we have been doing regarding massive high spin amplitudes in flat space. I'll try to give a general introduction to the problem, and then I'll present a very simple case. But the most general computations that we have done are very long to present in the slides. So I will request you to look at our papers. So this has been done in collaboration with two of ISO students, Mahesh and Raj. And I can't think of solving this problem without them. And what happened? And we reported this in this archive article, which has recently appeared in JHIP. Okay, so before I go into the motivation, let me try to define the problem, that what problem we try to solve. So I told you I will be talking about high spin amplitude. So let me define what is high spin. So we have been hearing a lot of talk here on flat space holography and all this, but so one part of it is that in flat space, the symmetry group consists of translation, rotation, and boost, and all this together is known as the Poincare group. And a definition of a quantum particle is simply a irreducible representation of the Poincare group. Okay, then from the representation theory, it follows that quantum particles are uniquely determined by the Casimirs of the Poincare group, which are known as the mass and the spins. So in 3+1, there is only one spin, but in higher dimension, there will be more spins depending on the number of Casimirs. Okay. So in general, in n+1 dimension, the number of spins is basically the floor function of n/2. So in the literature, for some reason, any particle that has spin more than 2 is known as a high spin particle. So whenever I refer to high spin in this slide, I mean any particle which has spin more than 2. And in 60s, Weinberg, and later there is a work also by Weinberg and Witten, which basically showed that higher spin particles cannot be massless. So they're necessarily massive. And I believe that's one of the reasons that though this problem is simple enough, were not studied in foundational days of quantum field theory. Okay, so my goal, having set up this terminology, my goal is to give you a closed form expression of tree-level amplitudes with arbitrary massive spin J exchange. So if I can use a Feynman diagram, then what we are trying to do is that we are looking for tree-level diagram. At this point, only 4-point functions, though I believe this can be generalized to higher point functions. With massless external legs, again, this can be done with massive external legs, but massless external leg is basically the motivation. When I'll talk about the motivation part, you will see it coming from all sorts of very exciting work. Some of them are India and some of them from outside India. So we are looking for a 4-point function where these legs are massless, external legs are massless, and this exchange particle is an arbitrary massive spin J particle. If they are scalar, the expression is very simple and easily available. We are trying to do when the external legs are spinning. Okay, so that's the question that we had tried to address. So once I have defined our question, let me try to give a very brief motivation that why we are looking into this problem. And again, as I said, that I only mentioned work of few, but there are many exciting work going at this point. And if you can mention that this work is in directly connection with some of the exciting things that people in the IFR are doing. So let me elaborate on that. There can be many motivations, but for me, the motivation is roughly coming from understanding what Suman mentioned about the CRG conjectures, theories of gravity. So last year, Penrose got the Nobel Prize, and we know that the important work of Hawking-Penrose singularity theorem, which basically says that the classical dynamics of gravity from a generic data, not from a very specific data, typically produce singularity, right? Though the singularity is inside an event horizon, but it produces a singular configuration, which basically says that even gravity as a classical theory is singular. So then, as all of us have learned in past, that whenever we have come across any classical singularity, we hope that quantization will save us. But in case of this, if we just take Einstein-Hilbert and naively quantize, I mention it naive quantization because maybe we have to be more smart in doing the quantization. But if we just do naive quantization of gravity, it doesn't help. It rather comes with more severe problem of non-renormalizability and all sorts of issues. Okay, so then the lore was that maybe higher derivative corrections can help us, because higher derivative corrections will not save us, will not change the nature of gravity at long distances, but it will change the dynamics at short distances. So maybe it will resolve the singularities. Okay, But as all of you who had at least 2 courses in QFT knows that any form of high derivative correction always comes with a new scale because they come with derivatives. So in my mind, at least there are 2 kinds of scenario that can appear, that the new length scale is the scale that is the Planck scale. It can well be true that all the high derivative corrections become important at the scale where the quantum gravity corrections are important. And in that context, whatever I am saying is not important, because I am assuming that there exists a length scale which is parametrically larger than the Planck scale. So for this talk, this is more or less an assumption. And also I am not aware of any work which has tried to prove that the scenario must be 2, not the 1. But if there is, and I don't know, please let me know. But I can just point out one analogy with the standard model, that in the 40s, there was this beautiful theory of Fermi theory of beta decay, which people turn out to be not unitary. It violates unitarity at some scale at 300 GeV. So that's roughly the scale that I think like the quantum gravity scale in analogy. And then when people tried to, people found standard model, people found that the new corrections kick in at 80 GeV, roughly 83 GeV, the mass of the W boson. So it always happens. In that case, there is an example, not in a non-gravitational theory, where the corrections kick in at a scale which is parametrically smaller than the scale where I expect the unitarity to break down. And there is this beautiful work of Satish Joglekar and other people who try to approach this problem in an amplitude way, and try to argue that how I can come up with a theory which is unitary at all scales, and it gives a Fermi theory of beta decay at low energy. And it basically shows that there are 2 possible choices, and one of them is the standard model that Glashow, Weinberg, and Salam got it. So our motivation is to do something similar in presence of gravity, though I must say we are very, very far from that. Okay, so in this direction, so I mentioned that a high derivative correction, and all of you are aware of this beautiful paper by these 4 gentlemen, Camino, Maldacena, Edelstein, Zubedov, who basically showed that high derivative corrections to gravity necessarily implies massive higher spin particles, and vice versa actually. So so that is their conclusion, and they and among many things they showed in that paper, which I not try to review because I think most of you know about that. But as all of you know, that this is not sufficient. This is a necessary condition that we should have massive high spin particle, but this is not sufficient, because really to have a good theory with all causality at all scales, we should have some form of restrictions on the 3-point functions and maybe on the spectrums. Okay, and for that I believe we need the explicit expression for the 4-point functions. Okay, so in this direction I mentioned this work by the KIFR group, where they tried to compute this most general 3-point function in various dimensions for 2 gravitons going to 1 massive spin particle, or 2 photons going to 1 massive spin particle. And that's basically you can take as our starting point for this work. Okay, so if 3-point functions are available, then what's basically the difficulty in computing the 4-point function? Because usually it's a very straightforward exercise. And actually I must say it is a straightforward but algebraically intense exercise. And this algebraic complexity, naive algebraic complexity, comes from the fact that the propagator for the spin J particle is a mess. It's hugely complicated. So it has this, I just flashed one transparency. And because of this big expression of the propagator, the computation looks hard at the first glance. Okay, it comes from the complexity of the expression on the propagator. So so with that thing in my mind, with that thing in our mind, we thought of taking the 3-point function and tried to approach this problem brute force. Okay, so before I go into again the explicit computation, let me just set up some more terminologies, which is I believe more general for structure of the spinning amplitudes. And So the most general structure of a spinning amplitude roughly takes this form, where I mentioned two things. One I called Ti, which is a function of polarization and the momentum, and this is a function of only the only the momentous. Okay, so this separation is usually called the tensor factors, and these are called the form factors. Okay, so for 4 scalar amplitude, this is just naively 1, and this is the full of the amplitude. Okay, but in case of spinning amplitude, there is more structure in it, and this index I is basically sum over all Lorentz invariant independent structures. Okay, so the sum over I depends on which amplitude we are interested in, and we'll see some of the expressions later. Okay, so as I said, that these F's are called the form factors and Ti's are called the tensor factors, we have to basically do the sum over all possible independent structure. But since I mentioned to you that I'll be mostly interested in massless particle, the basis we will always be choosing for this is a gauge invariant basis. Okay, for more general particle, the basis is much higher dimensional than for the massless particle. Okay, so with that thought, I just want to mention one more result. Again, it's available in the literature, and this provides an important cross-check for us that what the computation we did brute force is correct. And the cross-check is the following. It's only available to my knowledge in 3+1 dimensions, though there is no reason to not do it in higher dimensions as well. And it comes from the fact that massless particles in 3+1 dimensions are basically given by one quantum number. It's called the helicity. Okay, now consider a configuration where the two incoming particles are coming along the z-axis, one coming along positive z-axis, one coming along negative z-axis. And since it's a 4-point scattering, I can always map it to a xz plane or any two plane. I choose it to be xz plane. And let's say the outgoing particles are in the xz plane and at an angle theta with respect to the incoming particles. And let's say the four particles have helicity h1, h2, h3, and h4. Then using very simple methods, you can show it that in the center of mass frame, the expression for the tree-level amplitude takes this form. Okay, this constant is fixed. I have not given it in because of the space. It's available in our paper. It's explicitly known. The power of S is explicitly known. This is the pole part. There is a S power J factor, and this is the Wigner matrix that we have all studied in our quantum mechanics course. And the two arguments H and H prime are basically the difference of helicities. It's H1 minus H2. H prime is H3 minus H4, and J is the J of the exchange, the spin J exchange we are talking about. Okay.
Oh,
so
one question, Arnab. Sorry to interrupt. So this form is only for tree level or all loop levels? This will be the structure?
So if I go higher loops, then this pole structure is no more true. This will be more. Okay, this will be replaced by a more general function with all sorts of branch cuts and other things. But the angular dependence, I believe, is true in general.
Okay, and this n tilde will normalization will also change, right?
Normalization, the way we determined it, it's explicitly we have done using representation theory for tree-level amplitudes. Okay. Probably it's possible to do. See. You can always shift the sum of the normalization to the analytic, the function on S, right? Okay. Here the function of S is also very explicit, so all the numbers has a meaning. So in general, I don't know, in loops, depending on how you normalize the log function and everything, maybe this function can be determined. I have not tried that. Okay. Thank you. So this is an important cross-check that we'll be doing. Whenever we compute this amplitude that will go to center of mass frame, we put the expression of the helicities and we see that whether we get these expressions correct, whether we get these angular distributions or not. Okay, so now let me mention the method we adopted. I believe this method is known in CFT. and I will demonstrate it only for the photons, because the case of gravitons is just a double copy version of the photon. So and we did it in the paper, but for sake of explanation, we restrict to the photon for simplicity. Okay. So before I go ahead, let me say some few words about the 3-point function, and some part of it has been done by the IIFR group. So there are in the paper we define basically two types of dot products. One is this dot product with respect to the eta, which is a space-time metric, and second dot product is with respect to the theta, which, if you remember, I used to define the propagator. So theta is this one. Okay, so theta is basically the metric which is transverse, plane transverse to the particle. So theta is a metric in that. Okay, so it's related to eta, but it's not.
Just to get my bearings right, you're trying to derive that the expression that you just showed. Just go back to the slide that you just showed.
No. You will see. I am not trying to say, because this expression is only correct in the center of mass frame, and only for a particular choice of helicity. We are not writing down in helicity basis. We'll write down in terms of tensor factors and the form factors, which is not sensitive to particular helicity. It's more general. And if you put particular helicities, it will reduce to this expression. You will see. I will give an example.
Yeah, that's what I wanted to know. Okay.
So, okay. So we define these two dot products, and the reason for defining this is that if in our analysis, this O dot product is very important. Otherwise, we'll get wrong results. So again, the 3-point function of two scalars and one massive spin particle is this thing. This is the polarization of the massive particle, and these are the two massless particles which are scalar, and K12 is basically the difference, K1 minus K2. Okay, so now I will try to write down the 3-point function of photons with a massive spin particle, which, as I said, is known in the literature. It's not our book. So to do that, first I define these two expressions. Only if you are interested in the details, is basically this is the field strength, Maxwell field strength, and out of two Maxwell field strength, I define this object W, which is basically a particular contraction of two Maxwell field strengths of particle A and particle B. Okay, so this I will be using to write down our expression. Then the minimal 3-point function of photons with one spin J particle is this quantity. Okay, this is a very straightforward exercise, and it's known in the literature. Now, I just want you to look at this expression and just note one thing, that this expression, if I define this operator, forget about this normalization. So I first define this derivative operator. Then note this expression of the photon spin J 3-point function can just be obtained from the scalar spin J 3-point function through this operator. Okay, so this is our first observation, that the 3-point function in this case I wrote a minimal 3-point function. In general, for other 3-point function, this operator can be written down. I'm just doing it for this particular case. For non-minimal, it becomes even simpler. It becomes a multiplicative operator. And for other 3-point functions, we have given it in our paper. But the observation is that the photon spin J 3-point function can be written as a derivative operator acting on the scalar spin J 3-point. Okay. So with that thing, let's now move on to the 4-point function of the scalars. The 4-point function of the scalars is this expression. So if I take that expression of the propagator, if I contract it with the 3-point function, you get this. And again, this is a known result. And this reduces to famously the 𝗤𝗫𝗶𝗿 polynomial. And again, the normalization is well known. This is the normalization. Again, it's not our work, it's an old result. So now this is our main two ingredients that we used, this 4 scalar amplitude and the derivative operator. And what we tried to say in this paper is that let's say now I am interested in 4 photon amplitude. So these are 4 photons due to a massive spin J exchange. Then our claim is that the 4 photon amplitude is simply the action of the derivative operators on the 4 scalar amplitude. Okay. So let me summarize. From the information of the 3-point function, I get the derivative operator. And I claim that in order to get the 4-point function for more general 3-point functions, I just use this derivative operator on the 4 scalar 3-point function. 4 scalar tree-level amplitude due to massive spin exchange, and we will be able to do any spinning legs through this method. Okay. So let me proceed. Is there any question at this point? Okay. So with this, let me give a very simple example. This is the simplest example I can think of. Then let's now consider that. Yes.
Sorry to
yes, please.
disturb. Just to let you know, you are 20 minutes into the talk.
Okay. Thank you. Yeah. Yeah. Okay. So so let me now consider the case where we have 2 photons and 2 scalars. So I'm considering this case. Let's say these 2 are photons and these 2 are scalars. Again, 4.4 photon also can be done, and we have done it. But we are considering for simplicity that these 2 are photons and these 2 are scalars. In that case, we use this method. We computed the amplitude, and the amplitude takes the following form. Okay. So as I said, that there are 2 things. One is called the form factor and one is called the tensor factors. Okay. So these are the tensor factors, which is in terms of the W that I written before. And the form factors are explicitly can be computable, and these are these we have written down in terms of the derivatives of the Gegenbauer polynomial. Okay. So I just give you one particular example. But in the paper, we did all possible cases with massless particles. I'm sorry, I forgot to mention that we only did the symmetric traceless exchange. We're trying to do the other possible exchanges because we believe it can be extendable. And these are the things we computed. The main goal of the paper was to compute the four graviton amplitude. The 4 graviton amplitude seems to have 19 different tensor structures. And the explicit expression, it took us almost 2 pages to write down, so I'm not showing it. And as I mentioned that we did it for the minimal coupling because somehow the 4-point function computation is hardest for the minimal coupling. For non-minimal coupling, it becomes a much simpler computation. And in many cases, and some of the non-minimal couplings are available in the paper written by the TIFR group, and it just becomes a multiplicative operator. It's a simpler multiplication for the scalar amplitude. Okay. So this is our computation, and I will end with some very some more comments. So firstly, this derivative structure is though just a very algebraic tool in case of field theoretic amplitude, but probably this has some meaning in the case of string theory, where we already have a spectrum generating algebra. So a natural question to ask, and this question was posed to us by Ashok Sen, that can we generalize this algebraic structure for string amplitudes? Can I compute any string amplitude in string theory starting from just 4 scalar amplitude? Okay, and on that note, one can ask that it does it have anything to do with the higher spin gauge invariance and all sorts of things that, for example, Gross and Mende was talking in the 80s, late 80s. Okay. As I already mentioned that we did this case only for the symmetric traceless exchanges, and it's only a particular subset of the cases. There are more general exchanges and they're important, and they become only relevant in 4+1 and higher. But there is a reason to go to 4+1 and higher, because in 3+1, the scattering amplitude of massless particle is ill-defined due to the presence of infrared divergence. So if we want to, let's say, use some of these techniques to in the case of bootstrap and all this, then I think it's easier probably to go to higher dimension rather than solving the infrared problem in 3+1 dimension. But if we want to go to higher dimension, we have to consider these things into account, and which some of the things we are trying to do. And as many of you know, that in this paper, the authors tried to show that the 4 scalar amplitude is unique, and it's unique in a particular limit, which is an unphysical limit. A simple-minded question one could ask is that, can I do these things now with the 4 graviton amplitude? The main difficulty we're finding is just the mammoth structure of the amplitude. Probably there's a very clever way to handle it. Probably we are not clever enough to do that, but this is one question that one can do. And the more ambitious question could be the following, and it's related to what Pranjal Pandey wrote recently a paper, that in string theory one can ask the question that what is the strength of the 3-point functions? And in string theory, the 3-point function strength is explicitly available thanks to Pranjal. But one could now ask in a bottom-up way, maybe following some strategies that the TIFR group or the Camino et al. Paper followed, that can I now constrain the 3-point functions? Can I say more precise things about the 3-point functions? And can I show that at least in some sense, the strength of the 3-point function becomes something like the string theory? Okay. So with that set of thoughts, I thank you for your attention.
Thank you, Arnab, for a very nice talk. We have some time for questions. So I see Somdata's hand is up first. So go ahead, please.
So how would you incorporate internal symmetry indices in these cases? Because in general, like the gluon for the gauge boson, you would have internal symmetry indices even for higher spin operators.
I think, honestly, I have not tried to incorporate non-abelian structures into that because in general, what happens in non-abelian, you have to, the good thing about this case is that we managed to write it down in a gauge invariant way for every channel. But typically what happens in non-abelian theory is that all the channels are important to ensure unitarity. Okay, and again, I believe there is a paper, I think Abhijit is one of the co-authors, where the gluon 3-point function, gluon with spin j is known. But we have not tried. I have not tried it, so I don't have much thoughts.
Also, you.
Sorry, Somdata, I see that there are multiple hands up. So let's move on to the next question by Sachin.
Hi, Arnab. You did it. You are doing in 3+1 dimension and covariantly, right? In momenta.
So Sachinda, we did it in our expressions are available in any dimension, but we could only cross-check with the angular distribution formula only in 3+1.
Yeah. So my question is the following: in 3+1 dimension, it is known that the covariant expression for Flatcher's amplitude even for 3 dimension. Even for 3-point function and the spinor helicity answers, they don't match.
Yes.
For 4-point function also, do you see the same puzzle?
For 4-point function, if I remember, there is a paper by this Nima and other people, this massive spinor helicity paper. Since you pointed out, I will cross-check it again, but when we put it out, we cross-checked with the available result for the helicity expression that those people written down, and I believe we reproduce the same formula.
Okay, so these are generally supposed to match only in light cone coordinates, light cone gauge, etc., etc. Those has been shown, but covariantly it's a puzzle still. But you're saying for 4-point you have checked.
Wait. So if you are saying, so firstly we are doing on-shell, right?
Yeah.
So on-shell expressions, 2 on-shell expressions can at most differ by a contact term, which is again has been classified the 4-point contact terms. So when I do this expression, we also subtracted off some contact terms because of the expression of the propagators. In some cases, not in all cases. So my claim is the following. I think what we managed to prove is that the expression that the spinor helicity people did and the expression we did, they are same in almost all cases. In some cases, if the external legs, not for massless particles, but if they're massive particles, we also tried with massive particles, then the 2 expressions differ by some form of a contact terms. That's what we found.
Okay.
The next question by Loga. Loga, go ahead, please.
Hi, Arnab. Nice talk. So I wanted to just ask one question. You calculated the graviton force scattering, right? Like you guys claim to have all the structures and so on. So can you actually, I was wondering whether you can structure to see whether is there some kind of a very specific higher spin interaction, which when included, you can kind of absorb this known non-denormalizability in gravity, like the Gourav Banerjee divergence and so on.
Loga, I am not aware of this divergence, so maybe I have to talk to you and then I can.
No, this is just a standard divergence that the pure gravity is non-renormalizable.
Yeah, pure gravity is non-renormalizable, but you are meaning the loop computations are non-renormalizable, right?
Yeah, the two loop computation by Gourav and Sagnati and so on. Just
yes.
Standard thing. So what happens is that, like, I mean, there's a way of thinking about it where you just, like, think about it as, like some plus graviton, 2 plus graviton go to 2 plus gravitons. You can just look at that scattering and you can kind of understand the divergence showing up there.
So I think what you are trying to say, in order to understand that, I also need to understand the loops of the massive particles, because otherwise the analytic structure of the loop, here is a pole, so it's not a local term, whereas your non-renormalizable terms are not local. So I think we have to, don't you think we have to look for loops? And we did not look at that very carefully.
Yeah, so maybe let me just say, so if the higher spin particle is very massive, you would think that this exchange diagram will become like a contact diagram.
Okay. Yeah, I think in that limit, we did not look at it, but I think it is possible to back calculate that what we could do to remove that divergences.
Yeah. So the question is
sorry. Yes, go ahead.
Can you say what higher spin spectrum? Let's say I say that there's a particular contact term which is generated by some massive higher spin which is absorbing this divergence. Can you say something about the spectrum of higher spins that are needed or things like that?
Yeah, thank you, Loga. We have not explored, but I think in that limit it's possible to understand that question. Yes.
Okay, Alok.
Hi, Arnab. Yeah, so just a small question related to your discussion with Sachin. So, I mean, in the spinor helicity basis, the 3-point coupling of two massless and one massive for any spin of the massive and any helicity of massless is unique. So why?
Yes, correct.
So why would we not use that? I mean, sorry, I was a bit confused. But I mean, wouldn't it be easy to use that 3-point coupling and to compute these 3-level amplitudes, or we missed something?
So if I understand correctly, that the result that available in the more general covariant way in all possible dimensions, if you take that result and if you go to 3+1, and
I meant in 4 dimensions. Yeah.
In the helicity basis, then it reproduces the massive spinor helicity results. Only advantage of using the result of the TIFR group is that their expressions in more covariant is not helicity dependent, and it's useful for our way of doing things. But if you actually try to take them and write in helicity basis, it agrees with the result of the spinor helicity.
So in higher dimension, the coupling is not unique. You're saying, like in 4 dimension, is that one? Is that?
No, I think even in that case, it depends. In the helicity basis, I believe it's possible to show that it's again unique. Because the number of structures...
We may not have spinor helicity in arbitrary dimensions, so that's why I was asking.
Correct.
Yeah.
But again, you can write down a massive particle in, let's say, d dimension as a helicity basis, and you can write down the helicity amplitudes, right? Not in spinor helicity, but you can write down helicity amplitude.
Right.
I have not tried, but what we played with this, it felt like that this particular case is still unique.
Okay.
And it's not, I only played with the result that's available from the TIFR.
Thank you.
Okay.
Akshay.
Hi,
Akshay, please.
Thanks for a great talk. Actually, my question was also about the contact terms. Is it, if I understand correctly, your formalism only captures the exchange interaction and not the contact terms?
Correct.
Is it possible to fix them in some way by either demanding like perturbative unitarity or something like that?
I have not thought, but there's a complete classification already of the 4-point contact terms, right?
Oh, in any dimension?
Yeah, I think, I mean, Abhijit can tell better. Yeah, I think, I think that, it's a complete classification of the 4 graviton contact term available. So the only problem then remains is to just determine the coefficient.
Okay. And is there a way of doing that?
So it depends. See, the propagated expression that is available in the literature for spin J, the theta I showed you, if you remember, eta mu nu over p mu p. There are actually 2 expressions. One people uses 1 over p square, one people uses 1 over m square. So again, depending on that expression, the contact term changes. The only thing that remains invariant is the pole term. So I think in one particular scheme of things, if you use our particular propagator, then yes, it's possible to determine the numbers.
Okay. Thank you.
Thank you.
Sandeepan?
Hi, Arnab. Nice talk.
Hi. Thank you.
I have one question and one comment. The question is actually, it looks like from your results and from your setup, it looks like the impact parameter space might be the right language to talk about this kind of amplitudes, because like from Koushik's paper, we know that in the impact parameter space, actually all the 4-point amplitudes, at least for at the tree level, they factorize us.
Right, I agree. Yes.
So, and is that correct? Like that's the right. Like
I agree with your observation. The reason we did not still write the reason to go for me to impact parameter will be to also to understand some more properties, like something from the bound, something from causality. And if I understand correctly, the 4-dimension impact parameter expression is logarithmic divergence. So I cannot trust the tree level result. So I was more interested into going to higher dimension, but then I need to understand more contributions to the 4-graviton amplitude.
Even in 4D, but it will be a log of like B is the impact parameter, but like since you'll have all the derivatives acting on it, like it will be completely fine. So that's just an observation. The comment is actually like there are some theorems about massive high-spin particles that are known. Probably they are your.
I think few of them you and some other people wrote down.
Yeah,
right?
so it looks like your results should be useful in that context. That's just a comment.
Maybe I should contact you, because we tried to look at that, and we tried for a bit of moment, but I looked at that, but I don't have any. It also looked to me that we can prove those results, but maybe I misunderstood some part. So maybe
we could talk separately. Yeah, that's fine.
Okay,
thanks for the talk.
Okay. Thank you.
Great. Thanks again, Arnab, for a very nice talk. And also let me thank the other two speakers of the morning session, Akshay and Koushik. So with this, let me hand it over to Alok.
Thanks, Abhijit. So let's reconvene in 15 minutes, roughly 11:45, please. 11:45. Thank you. By the way, if there are any speakers for the next session who would like to test their screen share, please go ahead. You don't need anybody's permission or to become a co-host to do that anyways. Thanks. Hi, Sheshansu, are you there?
Oh, hi, yeah, I'm here.
Great. So let's see. The first speaker is, I think, Partha Paul. Partha
Right.
Paul here?
Yeah, I'm here. Hello.
Okay, great. So maybe you want to test your screen share. If everything's
Okay.
working,
Okay.
go back and forth with slides.
Okay. Yeah. Can you see it?
Great. Can you please go forward and backward? Just to make sure.
It's working. No.
Now it's, yeah. Okay. Can you go back, please?
Hello. Yeah.
Yeah. Are you going back?
Yes.
Ah, yeah. Okay, great. All right. Thanks.
Okay.
Thank you.
Okay.
If you want, I can keep it up because we're going to start anyways shortly.
Okay.
So, Sheshansu, will you please decide when to start? It's entirely up to you. Thanks.
Okay. So as you said, maybe we can start at 11:45.
Sure. Yeah. I mean, maybe would you want to wait for a couple of minutes? It's entirely up to you. We have 35.
Yeah, we can wait for a couple of minutes.
Okay. All right. I leave it to you.
Yeah. Okay. Thanks.
Thank you.
Hi, Partha. Can you hear me?
Yeah, I can hear you.
Okay. Should we start?
Yeah.
Okay. Welcome back to the morning session. The next speaker is Partha Paul. He's going to talk about MHP graviton scattering amplitude and celestial OP.
Okay. So, Okay, so let me begin by thanking the organizer for giving me the opportunity to talk here. So here's the title of my talk: so the asymptotic symmetries and graviton scattering amplitude. So this talk is based on these two papers with Koushik Banerjee and 𝗤𝗵𝗀𝗀𝗀𝗀. I'll mainly be talking about the first paper, and I will just mention the result of the second one. Okay, so let us start with the introduction. The gravitational asymmetrics in four-dimensional asymptotically flat spacetime has a rich symmetry structure, and the symmetries of the asymmetrics, the gravitational asymmetrics, are the asymptotic symmetries of the bulk theory of quantum gravity. Now, it is it is well known for quite a long time that the asymptotic symmetries of flat spacetime are the BMS symmetries due to these people, Bondi, Bart, Meissner, and Sachs, which is basically the Lorentz transformations and the infinite dimensional super translation. And then later, actually, this SL2C transformations was extended to the local Virasoro algebra, which we call the super rotations by Barnich and Troisert. However, in the last few years, the study of the soft factorization properties of the tree-level asymmetrics for gravitons has revealed a much richer structure for asymptotic symmetries. For example, we now know that the asymptotic symmetry algebra also contains an SL2 current algebra. And quite surprisingly, the whole W1 plus infinity algebra. So in this talk, what we'll do is that we'll just discuss some of these recent developments and their use in bootstrapping the flat space asymmetrics. So here is the outline of the talk. First, I will review briefly about the celestial amplitude, and then I'll talk about the symmetry algebra from the positive helicity soft graviton theorems, leading and the subleading. And then I'll talk about the celestial OP in the MHV sector, and then I'll conclude with some summary and some open question. So, okay, so throughout this talk, I'll only be talking about the massless particles. So suppose you consider a scattering amplitude where n number of massless particles are involved, then the asymmetrics element, so the scattering amplitude is defined in this way, where this is curly S stands for the asymmetrics, and the sigma 1 to sigma n, they are basically the helicities of the massless particles, and this omega zz bar. So actually, this null momentum of the ith massless particle, this pi mu, they are that is actually parameterized in terms of this omega zz bar. Now, the space of all possible null momentum directions is parameterized by two sphere, which is called the celestial sphere, and this zz bar are the coordinates on that sphere. Okay, so now it is known that the Lorentz transformations which act on the four momentum p mu as the linear transformation, but it acts on the celestial sphere as the group of global conformal transformations, and this zz bar transforms in this way. And so now actually keeping this fact in mind, what we'll do, we'll just make a change of basis, which is known as the Mellin transformation. So you take this creation of the annihilation operators and make this integral transformation, and define a new operator, say phi epsilon h bar, which is inserted at point zz bar. And here actually this epsilon is plus minus 1 depending on whether this A is an annihilation or the creation operator. And this h bar are defined by this equation. So h is delta plus sigma by 2 and h bar is delta minus sigma by 2. And under this Lorentz transfer, under the Lorentz transformation, this operator phi h bar, it transforms like a primary operator on the celestial sphere of weight h bar. So you can see its transformation property given by equation 6. So once you define a new basis, then what you can do is that you can just recast your asymmetrics elements in this new basis, and that amplitude is generally called the celestial amplitudes or the Mellin amplitudes. And this has a nice property that under the SL2C transformation, it transforms as, for example, the endpoint Mellin amplitude transforms like a endpoint conformal correlators. So you can just write them in terms of these phi operators. Okay. So now, first, what we'll do, we'll just study the soft theorems in this new basis, and we'll just see what do they imply for the symmetry algebra. Okay, so let us first start with the subleading soft graviton theorem. So this is the subleading soft graviton theorem for a positive helicity soft graviton. So here you can see this S1 plus ZZ bar. This is basically the subleading conformally soft graviton defined in this way. So you just take the positive helicity hard graviton primary operator, and then you take this particular limit. You get this conformally soft graviton. And I think the rest of the things are like, for example, this h bar k we have already defined, like the delta k minus sigma k by 2. So okay, so now what we'll see from this subleading positive helicity subleading subgraviton theorem is that this implies an word identities for the SL2 currents. So in order to do this, what we'll do is that first we treat Z and Z bar as some independent complex variable, and then we expand this this S1 plus ZZ bar in powers of Z bar. Now the right hand side is at most quadratic in Z bar, so we just expand this S1 plus ZZ bar. By these three currents J1, J0, and J minus 1. So now if you substitute this expression in this equation, so then you can get the word identities for these three currents J1, J0, J minus J, J minus 1 Z. So now you have these word identities. So rest of the things is just the usual, like the way we do in the 2D CFT. So you can define the modes of these three currents. So I'm denoting these modes by JAN. So A runs over these three values, 1, 0, and minus 1. And N is any integer. So now one can also check that these modes satisfy this following algebra. This is called this is actually the SL2C bar current algebra, because one can check that the zero modes of these algebras JA0, they are basically nothing but the one can check that they are basically nothing but the L bar 0 for J0, and then L bar plus minus 1 for this J1 J minus 1. That's why I am calling them actually SL2C bar current algebra. It has recently been, actually I also want to point out that it has recently been shown that this SL2 current algebra, they can also be obtained as an asymptotic symmetry algebra of the bulk theory of gravity. And for more details, please see Nimani's talk. So okay, so we have seen that the subleading positive helicity subleading soft graviton theorem implies the SL2 current algebra. Now let us study the leading soft graviton theorem. So this is the leading soft graviton theorem, and it is written in the Mellin basis, that is, I mean, like on the celestial sphere. So here this S0 plus ZZ bar, so they are the leading soft graviton operator. So they are defined in this way. I mean, this is G plus delta is the hard graviton primary, and then you take this particular limit, you multiply by delta minus 1, and then you take this delta goes to 1 limit, then you will get this S0 plus. And now this pk, they have the following property, that if it acts on a primary operator, then it increases the scaling dimension by 1, meaning the delta by 1. Now increasing delta by 1 means that the HH bar increases by half. Okay, and this epsilon k is plus minus 1 for an outgoing or the incoming particle. Now so now actually we'll repeat the same thing what we have done for the subleading ones. So we'll just expand this S0 plus in terms of these two currents, because now the right hand side is linear in Z bar. Now we substitute this in this equation, and we get the word identities for these two currents P0 and P minus 1. Now one can define the modes. So this Pm comma 0, the second entry here is for this 0 or minus 1, and the first one are the modes, so they are the integer numbers. So and one can check that these modes satisfy this algebra, that is the super translations form an abelian algebra. Okay, so from the subleading ones we get the SL2 current algebra, and from the leading ones we got these two super translation currents, and now one can check that they form a closed algebra. This is like the different modes. This is the commutators of the different modes. So okay, so now so far actually we have discussed only the symmetry algebra coming from the positive helicity soft graviton theorems. Now one can ask the following question. What class of graviton scattering amplitudes in GR is actually governed by this symmetry algebra, which is coming only from the positive helicity soft graviton theorems. Okay. Here actually the image v amplitudes comes into the picture. So okay, so the tree level scattering amplitudes in GR has the following property, that if all the gravitons have this positive helicity, or like one of them has the negative and rest of them is positive, then that scattering amplitude is 0. So the first non-zero scattering amplitude is the image v amplitudes. Now it has the following interesting property, that you start with the MHV amplitude and you make one of the negative helicity particles as soft. Then due to this soft factorization, it is 0. So it implies that in this MHV sector actually there is no negative helicity soft graviton. So then this MHV sector should be governed by the symmetries generated by the positive helicity soft gravitons only. Okay. Okay, so now so I mean, like we have discussed the symmetry coming from the positive helicity soft graviton leading and subleading theorems, and we have also seen like what sector in the GR actually is governed by those symmetry. Now actually we'll first look for the null states in this MHV sector, because they play an important role in our analysis. So now actually here, okay, so here actually we don't have a really well-defined notion of norm. So what we'll do, actually we'll rely on the fact that the null states are also primary descendants. And later actually we'll also verify that these primary descendants, they decouple from the MHV amplitudes. So in order to do that, first let us define what are the primaries under the symmetry algebra, meaning that SL2 current algebra and the super translations. So if phi h bar is a primary, then they satisfy the following relation, that JAN acting on phi h bar is 0 for all n greater than 0. And as I've said, this A runs over these three values for these three currents. And for the super translations, so the first one is P A comma 0 when acting on phi h bar, it is 0 for all A greater than or equals to -1. And P A comma -1, it is 0 for all A greater than or equals to 0. Now with these relations, now let us proceed. So let us start with a primary operator, say G plus delta ZZ bar, and let us consider all the descendants of this primary operator with this particular weight, H plus 3/2, H bar minus half. Now one can check that there are only two possibilities. This is given by the phi 1, which is like the J1 minus 1, P minus 1 minus 1, G plus delta, and this phi 2. Now let us take a linear combination of these two descendants, and where this C is the unknown coefficient. So now we demand now I mean like so we want to see that under what condition this becomes a primary. So you just apply this operator J minus 1 comma 1, and if this is a primary, then this has to be 0, and it immediately tells you that C has to be minus delta minus 1. So we can thus say that this particular state, this is a primary descendant of this primary G plus delta under the local symmetry algebra with this particular value of C. One can apply the same technique and get a second primary descendant. This is given by this phi ZZ bar, and it is actually has weight H plus 3/2, H bar plus half. Yeah. So now inserting these two null states inside the correlation function, one can get the following differential equations. Okay, so here these L minus 1, P minus 1, and these, I mean, all these things actually they are the differential operators acting on these correlation functions. And since you have two null states, you have these two equations, and these differential forms actually have shown some of them. Like for example, J1 minus P when acting on this correlation function, how are they actually, how do they look like? So yeah. And now actually we have also verified that these two equations, we have verified that the second set of equations, they actually are satisfied by any endpoint MHV amplitudes, and these actually we have done it till the 6-point MHV amplitudes. Okay, so now actually we'll move to the OP thing. So we have we now see that how the null states play an important role in analyzing these OP. So okay, so let us write down the OP between two primaries. So two graviton primaries. One is with positive helicity, and another one actually the helicity is left like arbitrary. And let us write down the OP in this form. So now if you just then use those two differential equations, and you just get the two equations for these coefficients CPQ. Now these equations are actually of the form that ax plus by equal to 0 and cx plus dy equal to 0, and these two equations have non-trivial solutions only for these particular values of q and p. So if you just put this q of p in the OP, then you get this following structure for the leading order term. So what we can see that is that these differential equations are basically telling that what kind of primary operators can appear on the right hand side. And now on top of, you also have the global time translations. Now global time translations are generated by four operators. Four p is actually p minus 1 comma 0, p 0 0, and the 2 is the p 0 minus 1 and p minus 1 minus 1. So if you apply the p minus 1 here, actually you can see that the role of the time translation is increasing the delta by 1. So if you apply that p minus 1 here, then you will get a recursion relation again for this coefficient c minus 1 comma 1. And then with the help of the other two equations and this equation, you can actually solve this c minus 1 comma minus 1. It is given by the beta function that you can see. So thus the leading order OP is actually completely determined. Okay. Now once you have this leading order OP, so what you can do is that you can actually now try to determine the subleading ones, because you know what is the symmetry algebra appearing. Okay, so so I'll just here actually only mention the order 1 term. So order 1 term is like yeah, so I mean, like, okay, so you just see that at the leading order you have this OP, where the c plus minus is actually the beta function. And this, okay, so actually I have written this g plus g delta plus delta 1 in this way. I mean, so here it should be delta 1 plus delta 2, but actually p minus 1 increases delta 3 by 1, so that's why you can write it in this way. And then actually if you now let us write down, let us check what descendants can appear at order 1. So there are two descendants. Now actually you know that there is a null state relation between these two descendants. So actually you can just simply write down one of them because of those null state relation. So let us write down the subleading, the order 1 term in this way, and then you apply like the other operator, the operator j minus 1 comma 1 on both sides of this OP. So so if you do that, you can then you compare the terms at a particular at order order 1, j to the 0, j bar to the 0. So if you compare them, you can just see that the c prime plus minus is given by minus c plus minus. So that's in the same way you can also work out the higher order OP coefficients. And here actually I have only kept the first few terms. And now actually, okay, so this OP actually I have discussed completely from the symmetry algebra point of view. But actually you can also determine this OP in the following way. So you start from the MHV amplitude, and you first transform it in the Mellin basis. So then actually what you can do is that you can bring two graviton primary operators close to one another, and then you can get this OP. And you can check actually that you will that OP and this OP actually matches with each other. And actually in later paper we have shown that, okay, so I mean, like, we have only used the SL2 current algebra and the super translation currents. Then in a later paper we have shown that actually this OP is also invariant under the holomorphic Virasoro algebra. Okay, so yeah, so now actually like, let me summarize actually what I have discussed so far. So I have just discussed so far the symmetry algebras which are arising from the positive helicity leading and subleading soft graviton theorems. And we have also shown that these algebra contains null state relations, and they give rise to the differential equations satisfied by the image amplitudes. Now these differential equations also, I mean, like can be used to determine the leading OP coefficients. And then okay, so now actually there are some several open problems. For example, one of them is like, so I have only discussed the positive helicity soft graviton theorems, and but if you go beyond the image amplitude, say for example, then there will be the negative helicity soft graviton theorems. So now the important question would be like to determine what should be the symmetry algebra when we have both the positive and the negative helicity soft gravitons, say for example. Okay, so yeah, I'm done actually. Thank you.
Thanks, Partha, for finishing before time. Questions? So,
yeah, so can the OPE coefficients also be determined from the W1 plus infinity algebra of Schrödinger?
Yeah, actually, I mean like, but I mean like W1 plus infinity is like a bigger one than this SL2. So of course you can, right? I mean like that already contains this SL2 current algebra. I mean, W1 plus infinity is like including all the soft operators, like, so they also include the subleading ones. So yeah.
Okay.
Are there any questions? We have plenty of time. We have 5 more minutes to ask questions. Okay. Okay, if there are no questions, thanks, Partha, again. Partha, can you answer?
Yeah. Okay.
Pranjal, are you there?
Yeah, I'm here.
Okay.
So let me just share my screen. Okay, so is the screen visible?
No.
Is it visible now?
Yes.
Okay. Okay, so first of all, thanks to the organizers. And today I will be talking about modified celestial amplitude in Einstein gravity. This talk is based on the work done in collaboration with Gourav Banerjee, Sudeep Ghosh, and Arnab Rudra. So the outline of the talk is as follows. First, I will briefly talk about what are the conventions which we will follow. Basically, we will see what will be the variables used to parameterize the null four momentum and the three-dimensional asymptotic space-time. And then we will see how these variables transform under the Poincare group. And then I will mention what are the Mellin amplitude and how we define the modified Mellin amplitude. So these are basically the change of basis for the scattering amplitude. And I will also mention what are the motivation for doing this change of basis. Now then I will mention about the conformal factorization. So this is the analog of the soft factorization of scattering amplitude in the case of the Mellin and basically the celestial amplitudes. And finally, I will sum up with a specific example of four graviton scattering amplitude, how all these things come together. So let's begin. So in the for the Lorentz group, the SO3,1, this is isomorphic to SL2C. So now using the polymatrices, we can go from the vector representation P mu to the SL2C representation P. Now this will be this capital P is the representation of four momenta in SL2C representation, and this is how we define the norm. Now under Lorentz transformation, it transforms in the following way. And we see that determinant that is the norm is conserved. So now the null momenta can be parameterized in the following way with the help of these three parameters: omega, which is the energy scale, and the z and z bars. So the z and z bars, they parameterize the 2D space of null momenta direction. which is the same as the celestial space, which we will see in the next slide. So we have parameterized the null momenta, and these parameters under the SL2C, they will transform in the following way. Omega goes to this factor and Z goes to this. So this Z we see is this transformation is the same as the global conformal transformation of ZZ bar. That is just to say that Lorentz group acts as the global conformal group of the celestial space, which is Z and Z bar. So now we have till now we saw how we parameterize the null momenta, and now let's see how we will parameterize the three-dimensional asymptotic space-time, the null infinity. So null infinity is labeled using the Bondi coordinates u, z, and z bar. Here z and z bar are the coordinates of the celestial sphere, and u equal to t minus r is labels the retarded time. So again, as I said, that space of null directions and the celestial sphere are the same thing. And under Lorentz transformation, these Bondi coordinates transform in the following. The u goes to and z goes to this. And under space-time translation, z maps to z and z bar go to the same thing, and u goes to this function, which can be written. So this factor has is without z and z bar and z bar. So we saw that the Lorentz group acts as the conformal group on 2D celestial sphere. So we want to express the scattering amplitude in a basis sphere. It admits some interpretation as a 2D conformal correlator. So we write the S matrix usually in the momentum space and in the plane wave basis. Now, since we want it to be represented as a 2D conformal correlator, we choose a conformal primary basis instead of the plane wave basis. Now this change of basis from the plane wave to conformal primary wave is implemented by this Mellin transformation. So we integrate with respect to the energy scale of the null momenta, and this S is the usual scattering amplitude of massless particles, and where the momenta is parameterized with the omega z and z bars, and this is the helicity. And we integrate, so we are integrating over all the energy scale. Now, so it's as by the way we wanted, so that how we define it. So this transforms indeed like a correlator of conformal primaries under the Lorentz transformation. Here the lambda which we have introduced here, so they relate to the scaling dimension in the following way. The scaling dimension delta is 1 plus I lambda, and the conformal dimensions are given by delta minus sigma, and delta h bar is given by delta plus sigma by 2. So yeah. Now why we want to go from the Mellin basis to the modified Mellin basis. So the motivation for that can be like justify. With this example, so take a case of massless scalars, and the Mellin amplitude requires the conformal primary basis. So the solution for the Klein-Gordon equation will look something like this. And we see that the particle will be localized at q dot x equal to 0. And all the particles, when we write the Mellin amplitude, they are localized at on the same null hyperplane, which is q dot x equal to 0. And here qzz bar is the unit null momenta. So for the modified Mellin amplitude, we will consider a basis in which solutions can be localized on different null hyperplane. So here we add a factor of u, in the denominator in the conformal primary wave. And now the particles can be localized on different null hyperplane, because this u will be different for different particles. Now, how this transformation, this change of basis actually looks like. So up up to this factor, it was the same for the this S here is the scattering amplitude. And we have for the modified, we have added this exponential term extra to now this exponential factor also helps with the regularization. And with this shift, we can keep the integrand with respect to omega well behaved for large value of omega. So this is the regularization term e to the power minus delta s. As we said that the Mellin amplitude, we thought it to be defined on the two-dimensional celestial sphere ZZ bar. We can think of the modified Mellin amplitude as defined on the null infinity UZZ bar. And this is manifest from its transformation property under the full Poincare group, which is given by this. So under the Lorentz transformation, the modified Mellin amplitude transforms in the following way. And under the global space-time translation, it transforms in the following way. So we saw that the Bondi coordinates transformed. So this is the same way they transformed. And under the global space-time translation, we saw that the u went to is something like some factor of z bar, and some constant, and z bar mapped to themselves.
A quick question.
Yeah.
Under the BMS transformations, how do they transform?
I will under the so these are defined on the SEA, but in the transformation operators. So they will be defined with some function for example, the super translation. They will be like some function of some factor of ZZ bar and del by del u kind of thing. So that will be what operator will look like. So correct. For super translation, this f will be like it will be a generic function f ZZ bar.
I mean, has it been worked out?
So I have not worked that out, but I think the general operators have been worked out.
Okay, maybe we can discuss in the discussion session.
Okay. So now coming to the conformal soft theorem. So the energetic soft theorem can be given like this omega going to zero, the energy scale, and the n particle scattering amplitude goes to some factor and the n-1 particle amplitude. The analog for the soft theorem for the celestial amplitudes is the conformal soft factorization, where we take the limit with respect to this the lambda factor we introduced to be 0. So these are just the leading energetic and conformal soft factorizations. Now, so in the conformal soft limit, the modified Mellin amplitude is related to the energetic soft limit, where we use this relation to get a delta omega. So when we put this conformal soft limit, so inside this integral we get a delta omega n. So and this Sn is the scattering amplitude. So this is related to the energetic soft limit, and this is the conformal soft limit. Now to use this relation to get a delta omega, we require that the integrand should be well behaved for large omega. So in the case of the Mellin amplitude, the requirement is that the momentum space amplitude should be falling at least as fast as omega to the power minus b for b some positive number. But for the modified Mellin case, we have the exponential regularization term. So the UV behavior of momentum space amplitude is not so restricted. So coming to the example, so this is the scattering amplitude for the MHV amplitude in Einstein gravity. The main thing to notice here is that this condition that omega to the power minus b, the scattering amplitude should fall as like that. So that is not met because omega are more in the numerator. So the Mellin transform of this amplitude from momentum basis to conformal basis is divergent. But that is not the case for the modified Mellin case, where we can define the conformal soft limit because we had the regularization term. So the integrand remains well behaved. So the integrand remained well behaved because of this regularization term, and we get the following conformal soft limit. And here we see that under translation, this is the u is z mapped to themselves, and this is the only u factor we have, and this remains invariant under translation because this whole factor, so the change in it is proportional to z minus z bar, and there is a delta z minus z bar constant. So now the conformal soft factorization. So we get, as I said, that we will get a factor like this, del by del u kind of term, acting on the n-1. So we had the soft limit taken on the first particle, on the n-1 particle amplitude. And this is because we took, so this was the leading limit, and leading soft graviton is the Ward entity for super translation. So appearance of del by del u is just an indication for that. So finally, conclusion that the similar calculation can be done for gluon amplitudes as well, and and we saw that the modified amplitude behaves like a correlation function of operators inserted at different points of null infinity, like so the three-dimensional space u z z bar. And in the modified representation, so the time evolution is more explicit compared to the representation in Mellin basis. I think it was also discussed on day 2 in the discussion session that the time evolution in the Mellin amplitudes, the celestial amplitudes, is encoded in delta I, the scaling dimensions. But here in the modified representation, this time evolution is more explicit with you. So with this, I would end the talk. Thanks for the attention.
Thanks, Pranjal, for finishing before time. Question, Som.
So is there any way you can relate these amplitudes to the Park-Taylor amplitudes for the MHV amplitudes concerning gluons, for instance?
So this similar calculation can be done for gluons, but how to relate to so for the MHV gluon amplitudes. and yeah.
So, I mean, they should be related, right, in some way, because for the image amplitudes, we know that the Park-Taylor result is the actual result.
Okay, so I don't know what to say. So I have not like worked out that relation. So yeah.
Okay.
Are there any further questions? If not, let's thank Pranjal again. Gourav, are you there?
Yes, sir. Yes, sir. Thank you. Hello. Hello. Hello.
Yes,
Okay. Okay.
Yes.
Thank you, sir. Thank you the organizer for providing this opportunity. And first, let me
You can share your screen.
Yes, sir. Screen share. Okay. Now to my screen. Full screen. Now, is my screen is visible?
Yes. It's visible.
Okay. Today, I am going to present my recent published work with Professor Nabamita Banerjee. That is logarithmic correction to the entropy of non-extremal black holes. Okay, how to remove this? Okay, logarithmic correction to the non-extremal black hole entropy in n=1 Einstein-Maxwell supergravity theory. The basic outline of the whole talk will be as follows. First, I will present the basic introduction about the research work. Then, I will present the hit kernel methodology used in the research work. And we will have a general introductory about non-minimal n=1 Einstein-Maxwell supergravity theory. And then we will apply hit kernel technique to this non-minimal n=1 Einstein-Maxwell supergravity theory and compute some fundamental hit kernel coefficient, Srikant coefficient, and a particular Srikant coefficient will be used to determine logarithmic correction of non-extremal Carnot-Neumann family of black hole in non-minimal n=1 Einstein-Maxwell supergravity theory. So let's begin the talk. So from the works of Beckstein and Hawking, we have proposed that black holes are thermodynamical objects which possess a definite entropy, classical entropy given by area of this relation. But this entropy relation has a limitation which does not depend upon the matter field present in the black hole background. It is limited to two derivative terms. So considering the quantum fluctuation, the matter field and higher derivative term, this entropy, classical entropy, demands correction. And so a full quantum corrected entropy relation can be given as follows, where we are particularly focused in this logarithmic correction factor, and most importantly this C factor which encodes the matter field and the interaction in the background, which will be given by the host supergravity theory. And the rest of the terms will encode the high derivative correction and massive correction, etc. So logarithmic correction, these are leading order quantum correction which arises from massless field and their coupling with a black hole background at one loop level, and these corrections act as an infrared window into the microstates of black hole. A successful comparison of logarithmic correction between microscopic and macroscopic, one can test a consistent theory of quantum gravity. Although our work is limited only the logarithmic determination of supergravity theory in the macroscopic part. Okay, the whole plan of the whole talk is as follows. The objective is to determine the logarithmic correction to the entropy of non-extremal Carnot-Neumann, Kerr, Disney-Nostrom, and Schwarzschild black hole in n=1 Einstein-Maxwell supergravity theory. And for this, we will use hit kernel expansion technique proposed by Wasilewicz for this purpose. And we will determine firstly hit kernel coefficient, that is Srikant coefficient. And then we will utilize the third coefficient for determination of logarithmic correction of the non-extremal black holes. So first we will have a basic review about, we will review the hit kernel methodology presented by Wasilewicz. Hit kernel expansion is considered as an effective way to analyze the effective action of a theory. So W, which is a one loop effective action, is related to the connected differential operator lambda of a quadratic fluctuated action in this way. In order to study the spectrum of the differential operator, we impose the hit kernel K, which is a solution of fundamental equation which can be expressed as this this exponential of different kinetic differential operator. And here, in order to counter the divergence in the lower limit regime, we impose the UV limit epsilon, which is tuned with Planck length LP. So with this boundary condition, this heat kernel K permits a perturbative expansion in small s in this way. In this where A0, A2, and A4 are heat kernel coefficient. Although our work is particularly fixed on this S-independent part A4, which we will later used in this integration part, and we will determine the logarithmic divergence via this heat kernel coefficient A4. Okay. Now we will present the methodology how to compute this Srikant coefficient A0, A2, and A4. So beginning with the quadratic fluctuated action, which can be expressed as this way, where this kinetic differential operator lambda is something like this form, where positive is sign is for boson and negative sign is for the fermion. The lambda should be Laplacian and Hermitian as per the prescription of Vasiljevic. And this form of kinetic differential operator is to be made it to fit in this prescription of lambda, where G is the effective matrix and N is the matrix related to the derivative part, and P is the matrix related to the non-derivative part associated with this kinetic differential operator. And now here there is a new effective covariant derivative is imposed, which is related to the ordinary covariant derivative along with via field connection omega, which is relating the different fields of different spin indices. Now, comparing these two kinetic differential operators, one can evaluate the respective expressions of E omega I by the in terms of N and P. And a generalized field strength omega can also be defined in this way, which is associated with the curvature of the background matrix and as well as the connection field omega. So after computing all these intermediate ingredients, one can determine all the first three Srikant coefficient, that is A0, A2, and A4 by respective computing the traces of their respective intermediate ingredients, which is computed here. So in the above expression, we have, as we are particularly focused in Einstein-Maxwell system, so we have considered, we have put R is equals to 0 in the above relation as such a system satisfy the rigid flat space, and also ignore the total derivative which integrate to 0. So now we will start a basic non-minimal n equal to 1 Einstein-Maxwell supergravity theory, as we are particularly interested in Koushik family of black hole, which are solution of Einstein-Maxwell theory. In concept of n equal to 1 supergravity theory, ever black hole configuration can be expressed as coupling pure n equal to 1 supergravity with a vector multiplet, and a supersymmetric action of such a theory is well studied by Faraday. And it is a tabular format of showing the field content of respective bosonic and fermionic sector of a supergravity multiplet and vector multiplet of n equal to 1 supergravity theory. So in this theory, the one vector multiplet is non-minimally coupled to supergravity theory. And the action is supersymmetric action is well studied in the paper of Faraday. We have extracted the only one loop part of the action of this from one loop part of the action from this paper, although there is a 4 fermion interaction term is also there in their work of Faraday, but the one loop interaction from the 4 fermion interaction will vanish because of vanishing of background field in the Einstein-Maxwell system. So here one can see that the gravitational field is non-minimally coupled to Gaussian field. So we nomenclature this theory as non-minimal n equal to 1 Einstein-Maxwell supergravity theory, and rest of the notation have usual meanings. So arbitrary solution G mu mu satisfying the ordinary Einstein-Maxwell theory when embedded in n equal to 1 supersymmetric theory. Such a geometry satisfies rigid flat space and the following equation of motion and the Bianchi identity and the Maxwell equation. And these equations, these above equation will have a tremendous positive effect in simplifying the Srikant coefficient in terms of local invariant, that is background gauge field, and in DC and Riemann terms. So now we will imply the heat kernel methodology to any non-minimal n equal to 1 Einstein-Maxwell supergravity theory. So imposing fluctuation in the metric and gauge field in the bosonic sector of action, that is L is equals to R minus F mu, one can get the gauge fixed quadratic fluctuated action of the bosonic sector, this one. Now, imposing this field definition to this quadratic fluctuated action, this operation will ease the further computation of Srikant coefficient by shortening the expression of P, omega, and all the intermediate expression. This field definition approach of heat kernel is done in the words of Larsen, and we are motivated by their field definition approach of heat kernel, and we also impose this heat field definition to our theory as well. And in Larsen's paper, Larsen's work, they have computed the bosonic sector of n equal to 2 Einstein-Maxwell supergravity theory, which is same here in our case also, and reviewed their work and computed the Srikant coefficient of bosonic sector of non-minimal n equal to 1 Einstein-Maxwell supergravity theory as follows. The bosonic result of this field-defined edge heat kernel approach obtained perfectly matched with the bosonic result of the general, that is without imposing any this type of field definition. From our earlier calculator, on our earlier work, we have computed the same Srikant coefficient, but without any such type of field definition. Although in that, without using this field redefinition, the computation was very much large and tedious. So now, again, beginning with a similar approach, we will start with the fermionic sector of fermionic sector action, which is represented in this way. Now again, implementing this type of field definition in this action, where by using this field definition, the kinetic part of this differential operator is a little bit simplified, which has great which simplifies the kinetic, which has great ease in the further computation of Srikant coefficients. Now this operator is linear in form. So first it has to be made Laplacian. So doing this operation, the form of lambda will be something like this. Now, following the very same approach of heat kernel methodology, and the Srikant computation will be resulted as follows. So again, the result obtained from this again field defined heat kernel approach matches with the result of heat kernel as we have computed via general heat kernel in our earlier work, which checks the consistency of this heat kernel results. So adding the bosonic and fermionic sector along with the Srikant coefficient associated with the post part as well, the total Srikant coefficient associated with the non-minimal n equal to 1 Einstein-Maxwell supergravity theory will be as follows, where we will now in the next we will particularly take this A4 term and determine the logarithmic correction, which include logarithmic correction to the black hole entropy. So in order to determine the logarithmic correction of non-extremal black hole, we first reviewed the sense formalism to how to compute the logarithmic correction for non-extremal, for the arbitrary non-extremal black hole. Then we imply this formalism, the formalism to our Quaternionic matrix, and so the entropy of the black hole, the log correction of non-extremal black hole can be represented as way where the A4 is to be evaluated in the full horizon, full geometry of the black hole background, and this is a non-zero mode part and this is a zero mode part. This zero mode part is already been computed in various literature in the works of Sen and Ferrara, using all the results of the literature. Presented this schematic compact form of the zero mode term. So we used that schematic form for the zero mode computation and integrated our Srikant coefficient computed is into we use the Srikant coefficient here for calculating the local contribution to logarithmic correction. Here in the zero mode part, 3 is associated with the translation symmetry, and X is the rotational symmetry possessed by the black hole, and SU SY is the number of supercharges possessed by the black hole. Delta is 1 for non-extremal black hole and 0 for extremal black hole. So using this integration result around of one full geometry for the Riemann and Ricci coefficient tensor, where all the RH is the horizon radius and B is a scale which is related to angular momentum divided by mass of the black hole. the net logarithmic correction to the following non-extremal black hole for Kerr-Neumann, Kerr, Diesel-Nostrom, a certain black hole are as follows. Thank you.
Okay, thanks, Gaurav, for finishing before time. Any questions? Hello.
Hi, Gaurav. Have you heard of the name of the mathematicians Peter Gilkey, Kirsten, and Branson?
Gilkey, yes, sir. Yes, sir.
Peter Gilkey.
Okay,
So
okay,
I guess I know that there is this famous physics reports user manual of sorts by Vasilovich, but I think Peter Gilkey is basically I think the person that you may want to actually refer to when you talk about applications of the heat curve technique.
Actually,
right?
yes, sir. This you have said right. Actually, this Srikant coefficient result. This is A0, A2, N4. Actually, these are first determined by Gilkey's paper. So yes, that's it. Here I have should refer Gilkey.
Yeah, and Sheshansu, can I just have one very small query?
Sure, sure.
I apologize, Gaurav, for displaying my ignorance, but I mean, what is so special about this n equals 1 Einstein-Maxwell supergravity? Why do you guys?
Actually, sir, in the works of Ferrara, they have determined the logarithmic correction for n equal to 1 n equal to 1 supergravity theory, but those n equal to 1 supergravity theory belong to only consider only the minimal interaction part, not the non-minimal interaction part. So in order to motive to provide a because in the general action which is of general action, there is a non-minimal coupling of non-minimal coupling to gravitational field and Gaussian field. So in order to provide a concrete result in the macroscopic part for the n equal to 1 theory, we have computed this result in non-minimal n equal to 1 Einstein-Maxwell supergravity theory. And the works of Ferrara, they have considered only the minimal coupling, and it is due to their methodological limitations. So our result is concrete. That's why, and that's why you have computed it. And again, in the microscopic sector, one can also test this result from our result to if one wants to determine the logarithm correction in the microscopic sector as well.
Okay, thanks, Gaurav. Can you unshare your screen? Aranya, are you there?
Stop share, stop share, yes. Stop share.
Okay, can you share your screen?
Yeah.
Okay. So Aranya is going to talk about island page curve and subregion complexity. Aranya, please go ahead.
Okay. Yeah, so thank you. Let me thank the organizer first for giving me this opportunity to present my work in this conference. So I'll be talking about islands, page curve, and subregion complexity. And this is based on work done with collaboration with Arpan Bhattacharya, Pratik Nandi, and 𝗰𝗵𝗶𝗶. This will be mostly based on this paper, but I'll also flash a few results from our more recent papers in the last couple of slides. So we have already heard a couple of talks on islands in the previous 2 days. So islands are newly encoded regions in the entanglement wedge of the radiation subsystem after the page time. And this was work done. This result is due to the work of these authors. So the idea is that the radiation bath, especially in these papers, they considered a non-gravitational radiation bath, and the radiation bath gets access to purely bulk regions from the black hole side, starting from this page time. And this islands or this change of minimal surface is captured by the quantum extremal surface, which was put forward by Engelhardt and Wahl. So this change happens at page time. The main result of this change is that the growing entanglement entropy curve bends at some point, which is the page time, and we indeed get a page curve, which is different for evaporating and eternal black holes. So for evaporating black holes, it goes up, and after the bending, it comes back down to 0. Whereas for eternal black hole, it saturates after page time. So we want to ask a question that if we can know more about the fine-grained bath side of the state, evolving state, using inputs from quantum extremal surface. So remember that the radiation plus black hole will be our pure state. So if we are concentrating on the bath side, which is the radiation side, it will be a mixed state. We are looking at a evolution of a mixed state. So we'll be looking at complexity, which is basically a quantum information measure quantifying the complication of preparing any target state given a starting reference state. And typically in the literature of circuit complexity, one computes the optimal number of elementary quantum gates needed to construct this target state from a given reference state using these elementary set of quantum gates. There are also other proposals of complexity, for example, Krylov complexity, which Koushik talked about yesterday. And this is due to work of these authors. So for mixed states, what would be the definition of complexity? So usually complexity is defined for pure states, but for mixed states, what one does is, again, they purify the mixed state by adding auxiliary system parameters and consider all possible purifications. And numerically, we have to minimize the complexity functional with respect to this auxiliary system parameters that we add to the system mixed state to purify it. So the holographic duals of this complexity has been proposed by Seskhar Brown and many other authors. So the idea is to compute maximal volume slice, space-time volume, or the action of the Wheeler-DeWitt patch to get the complexity of the pure state. Whereas for the mixed state, the idea is to compute the subregion codimension 1 volume associated to the entanglement wage of the subsystem. For a time-dependent situation, one has to compute the maximum volume below all possible candidates of HRT. And this is due to the work of these authors. So what we will be doing is to look at volumes below the quantum extremal surfaces at different times. Especially, we want to see what happens when the page transition takes place. And we found in a previous paper that there is a jump in the subregion complexity at page transition point. So the idea is to have some general idea about the evolving radiation state. So this is the outline of the talk. I'll be talking about the model firstly, then the subregion complexity of the radiation, some other studies, and I'll end with concluding remarks. So recently there have been, in the models that Island have been studied, especially in higher dimensions, brain world models have played a major role, which are W holographic models, and Randall syndrome brain worlds with subcritical tension brains have come in there, especially the Karch-Randall brain world models, where the gravitons are massive. But in a recent work, also weakly gravitating bath was considered by introducing a second brain in the bulk, and gravitons becomes massless and localized on the weakly gravitating brain in this case. So the brain angles when two brains are present in the bulk dictate the strength of the gravity on the brain. So weak gravity would mean a less angled brain. For example, in this figure, this is taken from this paper by Gang and collaborators, and the right brain, which is in a lesser angle with the conformal boundary, is the weak gravitating bath, and this is the physical brain. This bulk region can be taken to be 0 temperature or black string configuration, thermal black string configuration. And for both of these situations, the authors found that there is actually, for a dynamical radiation, there is no diffeomorphism invariant way to differentiate between the local degrees of freedom. So we cannot, using the ideas of double holography, if we compute the RT surface in the bulk for this dynamical radiation scenario, one finds that for a vacuum solution in the bulk, the HRT is just a point, And for a black string configuration, it is the horizon over here. So, and there is no change of extremal surface in this picture. So for a weakly gravitating bath, the entanglement entropy is a time independent constant supported by previous flat space arguments by these authors in a paper, which says that all bulk information, even the information inside black hole, is present in an infinitesimal with Cauchy slice on boundary. But we will be doing something else with this model, which was also talked about in this paper. So they also studied something called the left-right entanglement, where they indeed reproduce a page curve, which is of the type of the eternal black hole. So no page curve for dynamical radiation with gravitating bath. However, they find an eternal black hole type of page curve for the left and right modes of the thermophile double state. So this red point is a d-1 dimensional defect safety, and there is a thermophile double state, so it has a partner defect mode on the other side. So there is a partition made on this defect modes, which they call left and right modes. And let's see how the degrees of freedom in the bulk or on the branes will react to this partition. So will the left and right modes be on the left and right branes? We'll know more about this in a while. So they consider candidate RT surfaces, and the idea is that always they have to end on the defect. There is no other constraint on the partition of left or right modes, but the RT surfaces have to end on the defect. So there can be two kinds of RT surfaces, one going from this defect to its partner defect, which is the Hartmann-Maldacena-Mathieu surface, which grows indefinitely, which is this black line. And there can be other kind of surfaces which end on the left or right brane. In this case, one finds that particularly there is a surface which ends on the left brane, which after some time can be the minimal surface. So initially the Hartmann-Maldacena-Mathieu surface is the minimal surface, but at some later point of time, this surface, which we call the island surface, becomes the minimal surface. So there is a transition happening, and we reproduce this eternal black hole page curve. So
Aranya, you have got 5 minutes.
Okay. So after the minimal surface shift from Hartmann-Maldacena-Mathieu to island surface, some of the right modes appear on the left brane as well. Beforehand, all the right modes seem to be on the right brane, but after this transition, some of the modes also, right modes are seem to be present on this part of the left brane. Okay, so when we compute the subregion complexity below the surfaces, we will use this proposal, where the covariant proposal, where we look for codimension 1 bulk slices with general, so it will be anchored on the boundary, but it can go to other times apart from the boundary time. And among infinite number of such slices, take the one with the maximal volume. So we compute such volume, and we find that initially the Hartmann-Maldacena-Mathieu volume is this region between the right brane and the Hartmann-Maldacena-Mathieu surface. So right brane here is the analog of the radiation region, which gets access to some new modes after the page time, what we call the page time. And there is a jump at page time, which is this region getting added to the entanglement wage of this right modes. And this newly added volume also grows with time as it involves beyond horizon region. So this region will also have beyond horizon regions. So what we find is that the complexity keeps growing. The complexity of the analogous to radiation region keeps growing. And there is a jump at the page time. And this jump itself keeps growing after the page time as well. So here we have just plotted the change of this from this plot to this plot, and after the page time as well. So this jump keeps growing. So let me mention a couple of other related studies, which is in a very recent paper that appeared yesterday with our new paper. In that we have studied a model where the bath is the conformal boundary, and we deformed it by introducing scalar perturbations, resulting in a set of RG flows Schwarzschild to Kastner in the near singular geometry. And the jump is found to be related to the page time. So if we increase the scalar parameter, the page time seems to increase and saturate at some point. And we find that the jump also shows similar behavior. It decreases and saturation saturates at similar point of time, scalar parameter value. And in an earlier paper, we showed that in a multi-boundary wormhole model, even if we have access to a part of the radiation subsystem, even then there is a transition of the QES surface corresponding to this half of the radiation subsystem. But this transition happens at a much later time than the page time. Yeah, so these are two just results. So I'm maybe running out of time, so let me conclude. So we compute left and right complexities where the system follows an eternal page curve of the entanglement entropy. At page transition point, subregion complexity goes through a jump right for the right brain and a dip for the left brain, consistent with previous studies in one of our papers for evaporating black holes. And quantum extremal islands made easy part 3 complexity on the brain by Myers and collaborators. The jump has the following plausible explanation, that it is due to the explicit purification of the modes between the island side and the radiation region. So this we call the auto purification. We don't have to introduce an auxiliary system to purify the mixed state here. Some part of the mixed state gets auto purified due to this inclusion of the island region. So this volume corresponding to the right brain after page time keeps growing forever, with the slope increasing a bit after the jump. But there are a few more questions we can ask, which is this universally found jump seems to depend on the page time inversely, as we found in our most recent paper. So what else does it depend on? We also don't have a very clear idea from these models that what does page time itself depends on in these models. So it would be interesting to filter out physical information from these fairly different models that people study for these island situations and look for more universal features within these models. Okay, that's all. Thank you.
Thanks, Arnab, for finishing in time. Questions? Okay, if there are no questions, let's thank Arnab again.
Thank you.
Parthiv, are you there?
Yes. Can you hear me? Am I audible?
Yes, you are audible. Can you please share your screen?
Yeah. Is it visible?
Yes, visible. Yes, it's visible. So the next speaker is Parthiv Haldar. He's going to talk about lessons from quantum information to S-matrix theory. Parthiv, please go ahead.
Okay. Thank you very much first to the organizers for giving this opportunity to present the work. So my talk is named Lessons from Quantum Information Theory to S-matrix theory, to quantum information to S-matrix theory. So before I start, let me give a brief review of the playground on which we are going to play. So S-matrix bootstrap is a very old idea. It was first conceived by Werner Heisenberg, who wanted to develop a theory manifestly without the infinities of the quantum field theory, which today are handled by renormalization theory. Building upon his philosophy in 1960s, Geoffrey Chew championed the S-matrix bootstrap in order to construct a theory of strong interaction. That time QCD was not developed yet. Using the basic requirements of unitarity and analyticity for S-matrix, because from an experimental's point of view, S-matrix is the observable, field is not the observable. While Chew's original goal of QCD did not take off, the old S-matrix bootstrap actually paved way for the birth of string theory. The program got a modern revival in the computer-friendly 21st century following an impressive success of the conformal bootstrap program, which is similar program, but in a sense a younger, aided by modern numerical tools of semi-definite programming. You can see all these works, it's been going on for some time now. Apart from the numerics-assisted revival, attempts have been made to revive the analytics as well in the modern settings. The main objective of the current state-of-art S-matrix bootstrap program is this. It's to constrain the space of physical theories in a self-consistent manner. In a self-consistent manner in the sense that you start with some basic physical principles like unitarity, analytic structure, which is essentially a manifestation of causality, possibly other principles to to kind of see where do the physically consistent S matrices lie, and possibly to explain why standard model is so special. Now, where does quantum information fit in the S matrix theory? In recent times, we have seen that insights from quantum information theory have been extremely successful in the realm of high energy physics. S-matrix theory seems a very natural playground for theoretic analysis because scattering invariably changes entanglement structure of the scattered particles. The question is whether QI theoretic investigations lead us to new constraint on the space of S-matrices and thereby possibly lead to some kind of selection principle, which will lead us to, to select one S-matrix over the other. So this talk is roughly based on this work from the past year and some work that's going on with Ananda Sinha. So what we hope to gain. So this is a picture of a result of S-matrix numerics that we did in this paper. This picture actually follows from some basic unitarity analysis, some analytic requirements. And this blue shaded region, this river-like region is the whole it's the whole allowed space from those constraints. Of course, you can add more constraint, you will be possible constraining. But quite interestingly, standard model seems to be living on this cross, which is like a kink-like position. So the question that you can ask is that can we constrain the allowed region in a non-trivial way using quantum information theory and possibly close on to this cross or standard model, in a rather non-trivial way. But how can we probe entanglement that is produced by scattering in a way which manifests the entangling properties of the S-matrix? I mean, what kind of measure we are going to chase after, which will bring out the entangling structure of the S-matrix itself? One quantity of interest, it's called entangling power, which was introduced by these people in the context of quantum information theory. So for a bipartite system, which with a state space, which you can factorize, where each of the Hilbert spaces are finite dimensional, if E is some entanglement measure over the same, I mean, it can be any entanglement measure which satisfies the basic axioms of the entanglement measure. Then the entanglement power with respect to E is defined by this averaging, which essentially is that you take the entanglement measure and average over all possible states with respect to some probability distribution P. Now, as an entanglement measure, these gentlemen, they took the linear entropy, which is like a simplified version of the usual von Neumann entropy. I mean, you can obtain this from the von Neumann entropy anyway. Why? Because it was actually calculationally easy. It was easier to calculation than a full-fledged von Neumann entropy. Physically, entanglement power really measures that how much entanglement you can import upon an otherwise entangled state. The important point is that for a given probability distribution, the entanglement power is essentially a property of U, because you essentially have averaged over all possible states. Thus, one can try to make an entanglement assisted comparison between different unitary evolutions in terms of this entanglement power. Now, for our analysis, we will be mostly concerned with uniform distribution. For uniform distribution, the entangling power actually satisfies a kind of bound, which looks like this. The interesting thing is this upper bound, which is entirely in terms of the dimensions of each subsystems, assuming one dimension is less than the other. Now, the idea of exploring entangling power of S-matrix is not new. It's been already considered in the context of low energy QCD scattering, which is by these gentlemen in 2018. And recently, it was also studied in the context of the S-matrix approach of the classical gravitational scattering, which has been quite some time. by Yutin Huang and collaborators in this work. And they found quite an impressive understanding where they showed that essentially a minimization of entanglement power leads to a very specific kind of black holes, black hole scattering. Now we consider, for our case, entangling power of S matrix for entanglement in the isospin case, in the context of 2-2 pion scattering. Why? I mean, for scattering, of course, you have various degrees of freedom. The most primitive degrees of freedom is momentum, but momentum is infinite dimensional, which is problematic. Then you can go for some, finite dimensional degrees of freedom, like isospin, possibly spin. We took isospin because spin is a little bit problematic for relativistic particles. Now, in this case, each subsystem is 3-dimensional, which is finite dimension. So, we hope to then therefore exploit the bound that I quoted before to constrain properties on this matrix. So a generic isospin particle state, we can see it as a Q-trit state. I mean, Q-trit is a 3-dimensional analog of a Q-bit. Now, the most general state, I mean, of a Q-trit, you can be represented by a point on complex projective CP2. So a single particle isospin state can thus be parameterized by this in terms of the CP2 angle, CP2 parameterization, alpha, beta, mu, and nu, where momentum P is now a very important label because momentum is always there. And this P -1, P0, P1, these are the base Q-trit. That means these are the, you can think of, essentially these are the eigenstates of the I3, the zth component of the isospin. So mu, nu, and alpha, beta, these angles satisfy these in range. Now, for the geometry, the CP2 in this, it's given a metric geometry with the usual Fubini study matrix, which has the differential volume element, which is given by this, and with a total volume equal to pi²/2. Now one can consider an initial state. So by construction, we have taken the state in such a manner that we are considering in the center of mass frame, so that the two momenta are in opposite direction. You can choose it to be in z direction or whatever, but with each of their alpha, beta, mu, nu parameters with them. Now, as a final target state, we will consider this state phi, which is obtained by first you act S on psi, but then you take a projection on the two particle state, because psi S acting on psi will produce a whole plethora of states, because you have essentially all kind of it can go to all kind of states, but you take a projection in two particle states, so that your final state is essentially two particle state, rather a superposition of the two particle states. Here, A, B actually corresponds to base Q-trits. Note that here, the important point to note here is that I have taken a particular momentum. So this Q is not equal to P, it's some other Q, but it's a particular momentum configuration. So it's not exactly a projection onto the total two particle state, rather it's a projection on the isospin sector of a two particle state for a particular momentum configuration. So that's an important point to notice.
I think you have got 5 minutes.
Yeah, okay, thanks. Now one can consider the density matrix starting from phi, the usual way construct, and obtain the subsequent reduced density matrix. And then one will have the entangling power with a uniform distribution over CP2, because actually 2 copies of CP2. It's not just CP2, it's CP2 cross CP2. So that you have this, division by 2 factors of CP2 volume, and an integration over the CP2, the entire CP2, each copies of the CP2 file. Now on this EP0, this is essentially a function of MST, which is the scattering amplitude. I mean, it's a complicated expression, but it's essentially a function of MST. But on this quantity, since it's a finite dimensional Hilbert space to start with, because it's isospin space, you can actually put the bound, put the bound that we quoted, because EP0 is supposed to satisfy that bound. But now that will transpire in terms of a bound on this MST. Now, how to analyze these bounds, because these are nonlinear bounds, this is actually in the numerics is work in progress. Finally, I would like to tell a little bit of what future directions one can take. One can consider what about the spinning particle, in general spinning particle, perhaps entanglement in helicity. For massless particles, perhaps one can consider entanglement in helicity. But for spinning particle, there is an issue of defining a Lorentz invariant, obtaining a Lorentz invariant entanglement measure, because it turns out that for spinning particle, you cannot really separate out spin and momentum. So in a sense, you have to consider the entanglement collectively in spin and momentum. So that's a challenging aspect of that. Secondly, perhaps, I mean, it's more natural, whether we can consider the entanglement power for the momentum entanglement case. But there is a problem that the momentum state is not only infinite dimensional state, but it's a very it's a different kind of infinite dimensional space, because it's already a very badly behaved space. So, you have to actually develop a quantum information theory in an infinite dimensional Fock space altogether. And finally, quantum information theoretic measures, they satisfy different kind of inequalities, like strong subadditivity or monogamy. The question is, which is worth interesting, is that whether these inequalities give the new insights to the recent programs of the positivity, because positivity constrain the space of ace matrices quite non-trivially, and whether we can obtain new insights into this positivity stuff from the Q information theoretic properties. The game is on. Thank you.
Thanks, Partha, for finishing in time. Questions? Sachin.
Hi, Partha. So, is there an example of let's say, S matrix which satisfies, say, unitarity and all the other constraint, but fails to satisfy, your constraint, or vice versa?
No. We have okay. So not explicit ace matrix, because anyway, so we are testing it right now. Stuffs with the pion data that is obtainable from this ace matrix bootstrap numerics. So far that does not violate things. But we do not have any other stuff, so to speak, analytically, because we don't know how to, right now, we don't know how to extract analytically anything out of it, because these are, we need to take help of the numerics anyway. So we don't know. Right
just to make sure, your S matrices, those are unitary, etc., but then on top of it, you put in this constant and you get something.
Yeah. Yes. Right.
Okay, so.
Yeah, so I was just wondering, why don't people consider constraining or bootstrapping the S matrix using the BMS symmetries, apart from the other Lorentz and translation symmetries? That would give far more constraints and kind of pin down the S matrix completely, right?
I don't know much about BMS symmetries, but I'm not sure whether a general S matrix is supposed to satisfy BMS symmetry or not. That I'm not sure. Because axiomatically, when you are looking from the axiomatic, because all this bootstrap, the entire S matrix bootstrap program was it's based on the axiomatic S matrix treatment. There, originally, you have unitarity and causality, so to speak. And causality manifests itself in terms of various analytic properties. Mostly, most precisely, it's a certain fall off in the infinity, the Regge fall off in the infinity. And people try to constrain that. Unitarity manifests in terms of positivity, but I don't know. I've never seen in the most general case, how does this BMS symmetry? Okay, first of all, I do not know about BMS symmetry much, so yeah, I can't comment on that.
Okay, Alok.
Hi, Partha. So my question is related to maybe Sachin's question. So the usual bounds we derive, for example, in the like angular momentum basis. I mean, the positivity constraints, they come from the usual postulates, right? So these are extra I mean, sorry, I misunderstood. So these bounds are, I mean, they are like reformulation of the usual constraints we will get from the postulates of S-matrix. So they are like
So this is an interesting question actually. So superficially, right now, with the stage at which we are, it seems like we are getting this is some extra constraint we are putting. But this is an interesting question altogether, that whether these constraints are already inbuilt inside the S-matrix theory. I mean, whether this can be. This can be proved. I mean, whether this is maybe this is nothing new. I mean, this is already there. Whether we will be able to prove it. I mean, that will be. So I think a rather interesting take can be that whether we can go in the. So one natural thing is obviously you start with the S-matrix inequalities or S-matrix properties, and you get this quantum information theoretic stuff, and oh, it's good. But I think a little bit more interesting would be that if you can go in the reverse direction.
Yeah, that was my next question. Because here it looks like you're only using unitarity, but if you go away, you can use analyticity and crossing.
Yes. Yeah, right.
Also, just one small question, that you varied the your state in the isospin space, but I didn't. I mean, can you have unequal masses? Keep the momentum fixed, but the masses are unequal, and then is it possible to generalize?
Okay. So you want to say that? Okay. Yeah, I think masses here is not really. I mean, because we could. I think the masses we can keep it like free. I mean, that's not a problem.
I see. That can be done.
Yeah. That's not a problem. Yeah.
Okay, Arnab.
Hi, Partha. Just very quick question. So I'm curious about your comment that you made in the last slide about momentum space.
Yeah.
So is there anything specific that you have in mind? In particular, for example, do you want to consider, let's say, shells of momenta, and you want to say that the Hilbert space has a factorization across those shells, and you want
to. So for example, this considering considering this entanglement in momentum, it's I mean it's not new. I mean, people have done before us, obviously. But usually we consider this like this Fock space states, like this this P states, this asymptotically free states. Now that is essentially, and you vary over the entire momentum space, and you get obvious infinities because your Hilbert space is infinite dimensional. But this is not. I mean, the way we work with the way all those Fock space states are, they are not even a Hilbert space. They are technically they are like the single particle state. There's not even Hilbert space. It's a rigged Hilbert space.
Right.
So I mean, so how do you? So for example, will there be a bound like that we obtained before? And after taking care of infinities, I mean, nobody have studied it. So I think you have to just work on it.
I was actually curious about whether you can, I mean, or how you define even operationally the density matrix and the reduced density matrix, for example.
Operationally we define in the usual manner. So suppose you have, so let's say you have a two particle state. So suppose you have two momentum, like, so just forget about the isospin and all that. You have just momentum. So it's like PQ. And then you have S acting on the PQ, but then as usual, you take a projection on the two particle states. Let's say KL, but then you integrate. So now when you're taking a projection, you have actually basically integrated over this KL states. Now from that phi state, you actually construct your density matrix, but now it will consider a bunch of momentum integrals. When you do the reducement, I mean, this you can do formally, of course. We do it formally. Now, obviously, you can ask more mathematical questions that we have not checked, but that's how people do it formally. Right?
Okay. So, I mean, I was just trying to understand whether you need a Hilbert space for this or just a Fock space is enough.
Yeah, I think Fock space. So we have worked so far in Fock space, but obviously, yeah, you can ask this question and how much mathematically they're correct. I mean, mathematical rigor and this question, that's a different thing.
Okay. Thank you.
Yeah.
Okay, Partha. Let's thank all the speakers for this session. Partha, Pranjal, Gourav, Aranya, and Partha for keeping in time. Let's thank them all.
Hello.
Thank you so much, Sheshansu, and indeed all the speakers. So let's reconvene at 2:15 again, 2:15, please. See you then. It'll be a post-lunch link. It's remember that. Thank you. I see a raised hand. Arnab, is that? Oh, no.
No, I just asked the question.
Yeah, okay. I thought you had a question about the session.
No, that's fine. Thanks.